Hello world, my name is David Malan.
And I'm Colton Ogden.
And we're here for the third live stream of CS50 2D, which is CS50's new and improved introduction to 2D game development, a successor to CS50G, which covered both 2D and 3D. More on the 3D part before long. Today will be a live lecture in the sense that we might start and stop and fix things, so please forgive if we make any mistakes. I'll be keeping an eye on the chat if you have any questions, and I'll raise my hand as needed to verbalize any to Colton. This course won't be available until later this year on edX, along with the assignments, but we'll follow up in the months to come when we are up and ready. Colton, curious to ask, we're in a 2-day game class here, but what was your favorite game growing up, would you say?
I really liked Legend of Zelda: Link to the Past for Super Nintendo. That was a big one. And you've played Zelda for NES and various
I am
other...
old enough to have played the original Zelda.
That's a good one too. That's a good one too.
I can still remember the sounds like when you use your sword to break through things.
Oh yeah, when you have full HP and whatnot.
Yeah, exactly. And in fact, it's the HP from Zelda that influenced the CS50 Duck's use of HP or hearts to throttle how many questions you can ask per unit of time.
I forgot about that. So. Yeah, that's clever. It's cute.
Yeah. All right. Well, give us just a moment to reset, and this will be CS50.
2.
Hello world, this is CS50 2D, and this is lecture 2, Breakout. So Breakout is a fun, I just realized didn't have the clicker in my hand, sorry. Okay, let's try it one more time.
No worries, no worries.
Apologize. Off to a not fantastic start.
Breakout star.
Alrighty, and 5, 4, 3, 2.
Hello world, this is CS50 2D, and this is lecture 2, Breakout. And Breakout is kind of cool. So in lecture 0, we did Pong. And interestingly, Breakout is kind of an extension of Pong. In fact, it was created by the same company, Atari, in the 70s. And there's a fun story also with Breakout. CS50 back in the day did a version of Breakout that was also a game and graphical. And I remember being involved in that project too. This is many years ago. But it's super fun. The cool thing about Breakout is that it allows us to take some of the things that we've learned in Pong, but also really get fancy with more complicated game mechanics and sort of levels and scoring. And it's also much more visually interesting, which I look forward to showcasing here in this lecture. But this is indeed, CS50 actually set the stage for this lecture many years ago. Our goal is going to be to produce something that looks like this, and there's a lot of pieces, as you might be able to infer. And so I think it might be best to demo the game itself. So I'm going to go ahead and step over to the computer. And let's just do a little demo here of the final example of our code. So I'm here in sort of the distro here, but if I go to Breakout 13, go down to main.lua, and then give it a start here, we'll see that we start off with some music to begin with, but also we have, at the very beginning, high scores, something to look forward to. If I click on that, we'll see we got CTO, CTO. This just happen to be my initials, AAA as well. If I go to start the game, we have a paddle select, so people might be seeing a lot of things in here that look quite new as opposed to the last few lectures, but I like the color red, so we'll go with red. I have it set to start at level 32 just to sort of visually typically showcase more interesting bricks, and unfortunately it doesn't look like we got some of the higher tiered variants in this instance, but I'm going to hit enter. It's going to move, the ball is moving, so it's going to bounce. We get sound effects, we have particle systems, some folks might have noticed when the bricks actually hit. So if I let myself take some damage, at the very top right of the screen, you'll see that we have a heart. Actually, I probably should have had you come up and demo, shouldn't I?
Oh, it's okay.
Do you want to do that?
Yeah, sure.
Yeah, okay. I totally just went into the zone. I'm going to go back I can go back to there and say we should start a demo, and then, or does it make sense to ask for volunteer here, you think?
I would just start over at this point. It's faster.
We say. Sorry, it was used to Pong 0, and then you did it yesterday, and I was thinking of Pong. Okay. So I'll start with something like, and then, so we got a lot of things here, but rather than talk about that, actually, do we remember the last thing that I said at the TV?
I would just start from the top, honestly.
The very top?
Yeah.
Okay.
And how Colton was able to adjust his volume.
2.
Hello world, this is CS50 and this week, this lecture we'll be doing Breakout, which is lecture 2. And Breakout has an interesting sort of history. Well, first off, it ties into Pong very nicely because it was created by Atari back in the 70s. And so it'll allow us to extend a couple of the ideas that we saw in Pong, but also CS50 proper did a version of Breakout back in the day, many years ago. And in fact, this was one of the first things that I worked with CS50 was adding sort of fun lasers that we shot from the paddle back in the day. But Pong and Breakout are, very similar in a lot of ways. But Breakout, as you can see, even just looking at this example, we have a whole lot of bricks instead of just one other paddle at the very top. And it is also a single-player game, which is kind of neat. And it allows us to look at a whole bunch of different things like scoring and levels and some nice visuals, which we'll take a look at today. So we can get a kind of an overall sense just looking at these screenshots of what the example is going to look like. But I think it would be better to actually demo it. And if I could, is anybody up to volunteer to give Breakout a proper try? Yeah, it's coming up. You look familiar.
Hi.
Colton, nice to meet you.
David, nice to see you again.
I'm going to go ahead and press this here. So, go ahead and stand on there. So, the arrow keys will allow you to move throughout the menu here. So, you've got a couple of options. Feel free to press enter on either one if you would like to. High scores and start both are different states now, game states. So here this is a paddle select. Right. The color you like.
Right. And hit enter once more.
We start at level 32 just to
good.
potentially give people some more visual
This is going to
variety.
go well.
And so it's very similar to Pong in a lot of ways. But as we can see, when the ball, for example, collides with bricks, we get these particle systems, these visual effects. Is a new update.
Clearly better at this than Flappy Bird.
We've got scoring at the top now. We didn't have scoring previously. Well, I guess we did, but now we have much higher numbers in our scores. We have health, which we even mentioned briefly.
The hearts at the top
very
there.
top, yeah. And then so if you were to, in theory, not be able to hit this ball. Okay.
Make it dramatic. Oh no!
Just barely got there. But you'll notice one of the hearts
life.
got detracted,
Yeah.
so that's another piece of game state, so to speak. And if we were to restart this and instead of choosing start, maybe instead if we were to look at high scores, we now have the ability to preserve scores.
Which one am I?
Unfortunately, those are all my initials in there. I should have let you finish. You would have beaten one of my scores there. But we have preserving of high scores to data, actually persistent data on disk. So a lot of new features this time around.
Right. I'll try again.
Well, thanks for giving it a shot. All right, as you can see, there's kind of a lot going on just in this example, this initial demo here. But we're going to take a more thorough look at all of these, of course. And some of the topics that we're going to see today, and we alluded to some of these at the end of the previous lecture, are, as some folks might have observed, there are a lot of graphics in today's example. A lot of, in particular, the paddles and the bricks and the background, all these different things, a lot of smaller graphics. And if we imagine just including all of those as individual images, it would be quite a lot. It would be very unwieldy. So we'll be looking at sprite sheets as a way to solve this problem. We had, and some folks might have noticed through rerunning the game a couple of times, but we have actually procedural layouts, meaning that all of our bricks as they're laid out are procedurally done. So that allows us to have very dynamic sort of game layouts. And every time you play the game, it's going to be a little bit different, which is kind of fun. State, of course, is important. The hearts were state, score was state, but also we had all these different states that our game could be in, the serve state, the play state, and we wanted to be able to carry that data across multiple states, as we alluded to at the end of last lecture. So I'll be looking at ways to do that. Levels, of course, we start on level 32, but typically you'd start at level 1, and then you'd work your way up. And as the level gets higher, typically it gets more difficult. We have health, which is another piece of state. Particle systems are a very nice way to add just a little bit of visual spice and polish to the game, so we'll look at a way to do that. Love makes that very easy to do. A couple of different forms of collision detection, which are different than the forms that we looked at previously. We'll look at that, both the ball and the paddle, but also now the ball has to collide with all these bricks at the very top of the screen, and that's going to require its own type of collision detection. And then lastly, persistent save data, those high scores. We want to be able to not just have a high score that shows right now, but if somebody else were to load the game up, we might want them to see our high scores in the future. And also, we might want to shoot for our own previous high scores and persist that data, so that'll have to live on disk. Now, Breakout as a game, as we saw, has a lot of states, a lot of game states. This is a topic that we explored at the end of the last lecture, and this is a state diagram that maps the entirety of Breakout. So if we recall, Pong and also Flappy Bird were quite simple. Flappy Bird only had 4 states in total, and this has, it looks like, 8 in total, and all of the, again, the relationships between them, all the transitional relationships between them are modeled here. So we'll just go through it really quickly, but we start in the start state. This is sort of like the all roads will lead back to the start state. But we can imagine that from the start state, we might want to go to the high score state, as we just did, because recall, at the beginning of the game, we go to high score. From high score, we can only really go back to the start state. It said press escape to go back to the start state. So that's essentially what we can do. And then there's another arrow. Notice that also these are unidirectional arrows. So these flows are all unidirectional. So if you go from the start state down to the paddle select state, if you recall, David selected the paddle that he wanted. It had different colors available to choose. Once we're in the paddle select state, we can then start serving the ball, which means we can move the paddle around, sort of like how we did in Flappy Bird. We had a countdown state. In Pong, we had a serve state, just to allow us to get a little bit of a buffer before we begin the core game loop. When we're in the serve state, we'll transition over to the play state by pressing enter or the like, and the ball will begin to move around. We'll be in the play state, at which point, if we were to, let's say, take some damage, which we illustrated, well, we want to give the player an opportunity to pause for a moment and then maybe regain their composure and then go back into the serve, and do that back in the serve state by going back into the play state after pressing enter. Once they're also in the play state, and let's say they were to clear out all the bricks in the level, which we didn't have time to demo, but if we were to actually clear out all the bricks, well, we need a way to up the difficulty and go to the next level. So we'll make a victory state from which we can then go back to the serve state to begin playing again. Now, if we're in the play state and we actually lose all of our health, well, we're probably going to want to go to a game over state, which is going to be a different path. And from the game over state, there are a couple of different ways we can go. Let's say we did not get, unfortunately, a high score. Well, we'll just go back to the start state. So we're back at the very beginning of our state machine. This is essentially the flow that will sort of represent the overall infinite looping nature of our game. And then if we're in the game over state and conversely, we actually did get a high score, we want to go into this new state where maybe we can enter in our initials and actually enter the high score or whatever name we want to place there for posterity. And then when we're in the enter high score state, maybe we want to see where we were in relation to all the other scores. So we'll just go right back to the state we already looked at, the high score state. And then as we saw previously, that has a unidirectional relationship transition back to the start state. So a little bit more complicated than prior lectures. Thankfully, most of those states are relatively simple, but I think it's important to have an overall bigger picture understanding of where we're going before we look at the minutia. So let's begin with Breakout 0, which is the day 0 update. Okay, I'm going to get just a drink of water really quick before I start. My mouth's already starting to get dry. Sure. Okay.
Today, were you planning?
All right, so if we go into my source code distribution here, which we were just looking at, transition over here. So there are all of the same updates are broken out into files, just like folders, just like we did last time. So one thing that we'll notice right out the gate, and I might have made a slide about this actually, in fact, is that Previously, we've sort of had all of our files in a hodgepodge, just kind of all at the surface, all in this one layer in our folder. And really, it's okay if we're doing something like Pong or even Flappy Bird, where things are a little bit on the simple side. But as you can see it shown on the slide here, there's kind of a difference between, there's an illustration between what this would look like if we were to sort of do it the way we've been doing it versus what I think is a more ideal way to do it. And this is kind of representative of what you might see typically in a game project. For starters, we have a source folder now. We're not just putting all of our Lua files at the parent level of our folder. We have a sounds folder, which I believe we did have in the prior lectures at the very least, but also a lib folder is interesting. Some folks might have seen that in other programming contexts for our libraries. This is a conventional thing and up to taste, but ultimately I think some folks prefer to differentiate their own project's code from other projects' code, like push, for example, in class. Those are libraries that we're using. So we'll just tuck those into lib. And then graphics probably should go in its own graphics folder or the like, or images, you can call it whichever you prefer. And then fonts as well, going into its own folder. And especially as projects scale and you have larger and more complicated projects with many different types of graphics and fonts and sounds and things, it's just very unwieldy. So it's better to try to consolidate things into sort of semantically meaningful folders, as we're doing here. And as you can already sort of see, we have a bunch of graphics and fonts and whatnot that I've already preloaded. Actually, just one font, but a lot of graphics, a lot of sounds too, if we open up the sounds. And these were all sort of pre-created, ultimately with BFXer. And folks can also use chiptone. All of these sounds are just freely generated sounds, very 8-bit inspired, ideally. And same thing, if folks might have also noticed a music track, same deal, except that was acquired from a public domain source quoted in the source code. So if we open up main.lua in Breakout 0 here, let's go ahead and condense that down. We'll see a lot of the things that we have been seeing previously, except now, one thing that folks might have noticed previously was that we had sort of all of our requires in one place in our main.lua at the very top of the program. And that can be okay. Again, for smaller examples, almost anything goes. People will be able to find their way through your project. But it's better often to try to consolidate individual blocks of meaningful code. In this case, rather than just to require everything, all of our dependencies, meaning classes and the like that we want to use throughout our code, it's better to put those all sort of in one central required place. In this case, we've created a file called source dependencies, which we can now see here. We have a new file, a constants file, because recall we did have a bunch of constants like our window width and whatnot. But we have source.stateMachine, which in this case is source/stateMachine, really. This is the way that Lua does paths with periods, with dots. And then we also have a couple of states to start with. And this is essentially more or less what we left off with at the end of last week when we were talking about states. But you can see that rather than just requiring these in main.lua, we can now put these in their own file. I'm going to go back to main.lua. So we have all the same things we saw before, love.load. We've got a random number generator. We've got a title. I'm putting all of our fonts again in those global tables that we can reference anywhere throughout our code, and they're given this prefix of G. We're setting our font to a small font. Remember, we have 8, a 16, and a 32. We've got all the textures that we'll need. We've got a window mode being set here, setting up push, all the things that we needed before. A lot of sounds in this example. And then remember, we ended with a state machine. So what I just talked about in the slides was all of the states that we were going to deal with today. And that was sort of where we left off in Flappy Bird, was the talk of states and state machines. And so the main place we're going to begin now, just to start off on the title screen, and I'm going to run this example so we can see what that looks like, is the start state. And the start state is just a simple graphic with some text. We have our FPS indicator at the very top left, showing 24 because I'm running at 24 frames for production purposes. But we have a couple of options here, just a start and a high scores. And notice that I can hit the arrow keys and I can move between them. We have essentially white for an unselected thing, and I'm choosing this sort of blue teal color to choose which one's highlighted, which is just a state variable. But all of this is just now encapsulated, as we looked at last time, in one central state object. So let's go ahead and take a look at what that looks like. I'm going to open up now. This is sort of a convention thing as well, and this is ultimately subjective. But I've decided, because states sort of feel like they could be their own category of source code, I've put them in their own folder called states within source. So in source.states, or source/states, thinking about it more traditionally, we can open up start state and see we're going to want to highlight start or high scores. In this case, when we press up, we're going to change highlighted to be either 1 or 2. We're using that ternary syntax we looked at last week. So if we're already highlighted, or if 1 is highlighted, then we'll set it to 2, else we'll go back to 1. So we'll just essentially toggle, almost like toggling a bit on and off, going between 1 and 2. We'll also, set up our love.event.quit handler. And so here is where we're sort of saying, OK, we're going to set the font to medium. We have a large font to say Breakout for the title. And then for medium, we're going to highlight, if 1 is highlighted, we're going to set our color. This is how we draw things in different colors. And then we're going to we're going to draw out with printf on the screen the start text. And that's because 1 is currently highlighted. Same thing down here. Well, except we're going to set color to 1111 to refresh in case 2 isn't highlighted. So we'll go to white. And then if highlighted is 2, we'll set it to teal. Or it will just be the 1 that we just set, in which case it'll be rendered as the off option here. So high scores will take whatever the color option is. Remember, anything that you're printing, anything that you're drawing that's a shape or even a texture is going to use this color, this set color, to sort of color it. If you draw images, it will tint them. But we saw, for example, rectangles and fonts. Those will all be colored by whatever this love.graphics.setColor is. So all we're doing is we're listening to keyboard input, and then we're highlighting which of the menu options to select. But that does sort of give us this beginning initial way to get into the source code, into our project. Now, probably one of the biggest things that we're going to look at in this lecture, besides the collision detection, which is a lot, is this idea of quads. Now, we talked previously just about images. Images are relatively easy to draw. We saw that last time. You just do love.graphics.draw and then whatever texture you want. But in this example, in this distro, we can see here there's just one paddle being rendered. And folks might think, oh, OK, well, we'll just include a paddle image. But we saw even just at the very beginning, well, we have a blue paddle, we have a green paddle, we have a purple paddle. If we want a bunch of different paddles, those will have to be their own image. But folks typically in industry find it a little bit easier to work with these things called sprite sheets or texture atlases, which will allow you to actually condense all of your artwork into one file, rather than have, if we were to make individual textures for each and every one of these images, this is maybe close to 100 or 50 to between 50 and 100 images. It would be very unwieldy. It would be horrible in code to be, OK, what's the name of this one? This is blue with green stripes, blue with yellow stripes. How do we even name these things? So folks have typically found it easier to use quads or UV coordinates, texture coordinates, to splice up individual images. We can just load one texture atlas, one sprite sheet, and then just think in terms of rectangles. Think about how to splice that up into pieces that we can then reference. We can say, OK, draw our main texture at this particular rectangle's offset, at this particular width and height. And that will allow us to pretend as if we have maybe 100 images, but in truth, we're just drawing one image. The graphics card is then taking those UV coordinates, that quad data, and just drawing a tiny little piece of that for us to make it seem as if we're drawing just that individual image onto the screen. And so the couple of the functions that we'll need to take a look at in particular are love.graphics.newQuad. And love.graphics.newQuad is just essentially declaring a rectangle. So it's not all that different from love.graphics.rectangle in terms of how we think about it, except it's a piece of data that's going to apply to our texture when we want to draw it with love.graphics.draw. Notice that we can pass in a texture, a quad, and an x and a y. So if we pass in a texture, then we pass in the quad rectangle, and then the x and the y. At x, y, it will draw our texture, but it will only draw the rectangle of that texture that we tell it to. So if we just define a bunch of these rectangles for the paddles, for the balls, for anything, any UI elements that we want, and then we just call it in this fashion, we'll be able to draw just small pieces of our texture onto the screen anywhere that we want. So why don't we take a look at how that actually works in code. I'm going to fire up an example here. I'm going to close out all of these existing files from last time, close this down. And then first off, let's just run this example so we see what it looks like. We can see right out the gate, it looks identical to last time, except if we hit start now, we'll see that we do have a paddle, and the paddle can move. And the paddle, in fact, is even set already to clamp to the x-axis of our screen, which is what we had to do with Pong. But recall, it was inverted with Pong. Rather, it was 90 degrees shifted in Pong, where you couldn't go up and below the top and bottom of the screen. In this case, it's just because we want the bricks to be at the top, and this is the way that Breakout was designed, we're clamping it down to the left and right edges of the screen. But this paddle is just being drawn now, not with a texture. Well, it is being drawn with a texture, but we're not just drawing an image straight onto the screen in its entirety. We're using a quad to delimit with UV coordinates essentially, which is just a way to represent fractional bits of an image on graphics cards. We're just drawing a piece of that texture and pretending as if we're drawing just the paddle as its own image, as its own entity. So if we look at right here in main, much of this should all ultimately be the same, but we've added a new state now. As we saw, we went from start to play by hitting enter on start at the title screen there. So the play state now, if you come into here, is going to have an init as usual, but notice that we've set self.paddle equal to a new paddle. So if we open that up, all of these things we're now thinking in objects, which we started getting used to in the last lecture. But a paddle, ultimately, it has a lot of the same things that the Pong paddles did. It's going to be very similar, ultimately, to the paddles from Pong, except now we're going to have, for example, this skin and size and things like that. These will be variables that can influence our appearance, and we'll look at how these work in just a moment. We also have a dx instead of a dy, because in Pong we had the dy. We're moving on the y-axis. Now we're moving on the x-axis, so it's a different axis of movement. We're moving all the same exact clamping logic that we saw previously using math.max and math.min to make sure we don't go off the left and the right edge of the screen. And then we are rendering our paddle here. And some folks might notice, and this is essentially what I just alluded to, that we have our gtextures main. So in this case, this is just our main texture. If we look at what that actually looks like here in our graphics folder, actually, it's going to be called Breakout, and we're just naming it main. But we can see this is the exact same texture that I just showed in the slides, and we're rendering the paddle, but we're not rendering this whole image when we draw, and that's by virtue of the fact, by the second argument, we have this G frames paddles. So notice that also we have a two-dimensional array here, which some folks might have seen in other courses, or a two-dimensional table. So a table can store keys and values, and those values can also be tables. So if you index into a table, and that also happens to be a table, you can then index into that table, and that's essentially what we're doing here. We're deciding to break up our texture into various named subtables into G-frames. So we can say, OK, I want the paddle frame at index x, index y. And that's essentially what we're doing here. We're shifting by doing a little bit of math to essentially find our, based on our skin and our size, if we look at the texture, if I pull that right back up again, graphics, breakout, we'll see in a second, we'll see sort of how we're splicing this up. We're going to have to do it a little bit manually because, you know, some folks might already be able to infer that the paddle, the bricks, for example, at the very top, are all a uniform size. And if we wanted to create all of the rectangles, we could just go through them iteratively, one by one, and define in hard-coded constants the x, the y, the width, and the height, and so forth. There's a much easier way to sort of dynamically, or rather procedurally, iterate through a texture based on the size of the units therein. But these paddles are different sizes, so we're going to actually have to do those manually. But what we essentially want to do is, depending on our skin, we're going to shift down by 4 rectangles to get whatever size rectangle we also want. We don't manipulate the size too much in this distro, but that will be one of the assignments, as we'll see towards the end of the course. We'll be choosing a paddle based on the size, or rather it will be manipulating the size maybe based on something like a power-up, making your paddle either bigger or smaller, depending on if you maybe have a penalty for touching some sort of poison mushroom from Mario analog in this game. Now we could also sort of cruelly elect to choose the first paddle here as the paddle we start with, but it's a bit harsh to do so, and so we've elected to choose this second paddle here, size 2. And so if we go back to paddle.lua, we'll see that at the very top, our self.size is 2, and ultimately what that's just doing is indexing into this array of quads that we're going to create, all these rectangles. So if we were just to choose the first rectangle in that array, it would be the small one. The second one would be the larger one. The third one would be the even larger one, and so forth. And so we're just doing some math here, basically multiplying by our skin, self.skin, minus 1, so that we can start right off on just blue, and 1, 2, 3, 4 will equate to the very first 4 quads. And then we'll just add 4 to that to offset depending on which skin we've elected to choose. Now, in order to actually create the quads, that's a whole different question. In main.lua, if we look over here, we'll see up at the top, we have in oops, sorry, G textures, G frames here. I've called it G frames because in a lot of circumstances, in most circumstances, when sprite sheets are chopped up and iterated on, it's for the sake of animation. We think of frames, but you could call this G quads, you could call this G recs, you could call this G frames, whatever you feel like. As we'll see, especially in later lectures, this idea is applicable to a great many different ideas. But in this case, we're just going to start with G frames gets a table that is going to start with a paddles key that has a return or has a value of this function, generate quads paddles, which takes in G textures main. So if we go over to our util file, notice in our dependencies, we do have now a require source.util. This is a common thing as well. You want utility functions that often do some work that might not be necessarily directly germane to the gameplay, but in this case, it is sort of data processing, and so it makes sense to have a util function or a util set of functions that we can rely on. I'm going to go to util.lua, and we can see here we have a general generate quads function, which we'll take a look at in a second. But we also have this generate quads paddles, which takes in an atlas. This atlas is just another term for a sprite sheet. Some people refer to texture atlases as like the original idea of an atlas being this collection of maps. And so a texture or a sprite sheet, a texture atlas, is sort of like a collection of other textures, a texture that is a collection of textures. And so that's why in industry you might see the term atlas used frequently. We're essentially going to, in this case, just iterate over from 1, starting at 0 to 3. And we're starting at 0 because we want to take UV coordinates are essentially based off of positional coordinates, very similar to how we move things around in the game world. So as we're chopping up our image, which is what this function is going to do, it's going to create those rectangles on top of our texture. We want to think in terms of regular coordinates. There's a little bit of confusion sometimes that can come about from Lua being one index with tables and certain types of loops that you'll see. But in this case, we're essentially going to, from 1 equals 0 to 3, which is the 4 different paddle colors or skins that we had, we're going to create 4 different sized rectangles based on all of the, if we open up the image again, just as a visual reference, we'll see it here. We can see that they're all different sizes. So if we imagine this rectangle is, in this case, 32 pixels wide, and then maybe 64, 128, 156 or some odd. Those numbers might not be exactly correct, but they're going to be a little bit larger. And ultimately, if we envision, per the slide that we looked at previously, these rectangles showing here, for the left one here, you can see it has an x and a y, so it's going to have some x and then some y value inside the sprite sheet. And it's going to have a width, and it's going to have a height. And that's what the quad is defined by. So we want this quad, we want this one, that one, and then this one. And then we're just going to put them all sequentially into one table that G-frames the G-frames paddles. And then individually, we can just reference them at 1, 2, 3, 4, 5, 6, and so on. And that's how we'll be representing all of the rectangles. So if we go back to the code there for that, util.lua, we can see we're using that function that we declared or we showed in the slides previously, which is love.graphics.newQuad. It takes an x and a y, so we're starting our x at 0, and then we're going to start our y. If we look up here, we say start at x at 0, and then y at 64. And then that's just down some distance on the sprite sheet. Then we're going to say it's going to be 32 pixels wide by 16 pixels tall for the first paddle, and then atlas get dimensions in this case, which is going to give love.graphics.newQuad the numbers that it needs in order to actually compute how to generate UV coordinates on that texture, so that when it tries to render the texture with the quad later, things will just work as they should. And in fact, now with newer versions of Love, you should be able to just swap this in as just atlas, and you don't even need the :get dimensions for right now. But either of those will be just fine. And then we're just going to incrementally just add 32 and 96. And those are the values that I was sort of alluding to previously. We're sort of shifting in our code kind of manually. Like, oh, OK, we know the first one is 32 pixels, so the next rectangle is going to be 32 pixels over. And then 96 pixels over, which is 32 plus the width of the second one. In this case, that would be 64 pixels. And then we go down to the next line, and this one is 128 pixels wide, the one that's one line below the 3 that are contiguous, and so on and so forth. And then what we're doing doing is we end up putting all of those into our quads table that we're creating here at counter. And we're just incrementing, going all the way down the line. And eventually, ultimately, we just keep adding 32 pixels down until we're finished with all 4 skin categories. And then we just return our quads table. And so in main, as we saw, generate quads paddles is therefore just going to give us back that table of rectangles, those quads or UV rectangles from which we can, anytime we call paddle render, which if we go back to that, or any function that draws a texture, we just draw the texture itself, which we've named main because it's our main texture. You could call it breakout if you wanted to, or whatever makes sense for you. And then gframes at paddles at, and then the math that is whatever our skin is, because they were every four paddles is a different skin, and then the size as well will be a sort of incremental index into those 4 paddles based on that offset. And then we are drawing it at x and y, and that has the result, once again, if I can show that, of rather than drawing the whole texture, we're just drawing the one coordinate at size 2, which was the flag that we were preserving. And we move it around, and we can think of it just like it was a rectangle, but it is in fact a big texture being drawn through just a window through a frame or a UV rectangle. OK, and take a water break very briefly. Okay, so with that out of the way, so one of the more foundational pieces in today's lecture, we can begin to start to add more interactive elements. So the first thing that makes sense is, well, we have the paddle. How about we actually get a ball bouncing around? And we've sort of looked at a lot of this already. And so this is Breakout 2, the bounce update, where we'll sort of add a ball here to bounce around on the screen. I'm going to go ahead and just move us over to looking at Breakout 2 real quick and get rid of all of these examples that we had. There are a lot of files, and this lecture represents a pretty big leap in terms of complexity. I think it's an important step for folks to get used to probably working in this kind of an environment, because code projects, game projects tend to be much bigger even than this. But do excuse the number of files as we bump up. But I'm going to go ahead and go into, not there, but in main. And then let's just run this really quickly just to see what we have that we're working with. I'm going to hit start here. And then we can see right out the gate, we have the ball moving sort of in a random direction. But this is altogether not unlike what we've seen with Pong, right, where we have a ball bouncing off of the paddle, and then it bounces off the top and the left and the right edges of the screen. Now, if we just let it keep going, I do believe it will just go on into infinity at the bottom edge of the screen, which is okay because we have to model the loss condition and health and things like that in the future. But we'll just quickly look over those pieces. And in fact, most of all of those folks will have already seen. Probably the part that folks might not have seen previously is we have this new function, generate quads balls. So this is going to take, instead of paddles, we want to actually have, as part of our texture, we do have all of the different balls, and there's different colors for them as well. So let's take a look at that here. If we go to graphics and we go to breakout, we'll see that they're actually baked into this same texture. The benefit of having an atlas, we can just point to any piece of this one image and they're all there, and we can visually also see, are all of our colors working well together? Does everything look good? And so they're maybe even slightly hard to see, but there are these 7 that are right here, kind of by the hearts as well, which we'll also need at some point in the future. Spoiler alert. But we can choose any of these colors if we want to. So very easily, also, the benefit of this is not only do we have just ease of general at working with code in terms of getting every individual sprite, every individual graphic that we want from a large collection, but there's just an impetus to add color and variety and various visual elements to your project, because it's relatively trivial to just create a whole bunch of rectangles and then just choose, okay, I want this skin, or I want this image here for this thing instead of this other one. You don't have to load in this new texture and do all this stuff. So I'm going to go ahead, go back to main.lua, and we do now have in source a ball.lua. So it's going to be largely the same. It's going to take a skin as an argument, so we can decide to parameterize the ball with a skin if we want to and make it random. But in this case, we also have a collides function. This is the exact same AABB we used with Pong, but ultimately this assumes that it takes in a target rectangle. And this will also decide if it bounces off the walls. So here it's the same code with Pong again, just in this case, also the top of the world as well. That's what this self.y less than or equal to 0 bit is. So that's just the top of the wall. If it hits the top of the wall, we also want it to bounce down. If it hits the left or the right, again, we're inverting the dx. And if it's the y, the top of the ceiling of the game, we want to invert the dy and otherwise keep it moving in the same direction. Play some sounds, things that folks should have ultimately already been seeing. But these are all largely, with the exception of the quads function, which again, if we take a look at that as well, I'm going to go ahead and open up, it's in our util file. We come down to generate quads balls, right down here. It's ultimately going to be a relatively manual process. We don't have to fixate too much on the details, but we're going to essentially figure out creating an x or they're 8 pixels wide and tall, which are these 2 parameters here. But the x and the y are going to sort of be manually hard set based on the indices into the sprite sheet. That's sort of one of the drawbacks of having a sprite sheet that has multiple different sizes of textures. You do have to do some amount of manual work at times. You can't just do a loop that'll just iterate through the entirety of your texture. The balls, recall, we're in sort of like a defined small space right directly adjacent to all of the bricks, and that's totally fine. You'll just sometimes have to do some manual work to programmatically extract them or to turn them into UV coordinates. And that's all we're essentially doing with these loops. Very similar in spirit to what we just looked at. Folks can look at it if they want to on their own perhaps, but it is essentially the same logic, just taking an x and a y, adjusting it by some amount, and then also adding 8 by 8 pixels to create those windows, those little the little rectangles themselves in a group, and then grabbing 4, and then grabbing 3, because recall it was 4 balls on top of the 3 in that example. And with that, we have the ability to then just render whichever ball skin we want to, and then render play the game and use it just as it were a Pong ball, for example, and it functions identically. So that's the extent of Breakout 2. So now, if we transition over to Breakout 3, this is going to be a little bit more of an exciting sort of update. So Breakout 3 is the brick update. And so folks might have already noticed that Pong is sort of this two-player game where you have a paddle versus a paddle. They bounce a ball between them, and then the goal is to get one ball to go past the other end of the screen. In Breakout, the goal is a little bit different. It's to actually break all of the, I believe the original theme of the game was you're breaking out of prison or something like that. And so your goal is to break through the bricks of the wall in your prison cell. And in this case, we'll sort of imagine something similar to that, but probably more of an abstract idea. We have these colored bricks that are just in space, and then every time we bounce off of one of them, no matter which direction, we want it to bounce off, and then we want to clear that brick. Or if it's a higher tiered brick, we might want to, for example, if it's green or red, maybe the different colors represent the tier or the hardness of that brick. And so hitting it once might actually reduce its color back down by 1, therefore maybe giving us a high amount of points, and then also keeping the brick in play so that we can still hit it again, and then eventually when it gets to the lowest color tier, then remove it from play. But then this gives us sort of difficulty in a sense, and also just visual variety, as we saw previously. Having a bunch of different colored bricks gives you a bunch of different ways to visually just present ultimately a refreshing and dynamic playing field. And we'll look at what's really cool in this lecture is the randomization of what that could look like with a level maker, which we'll see pretty shortly within a few examples. But to start with, as we can see just looking at the slide, it's essentially a grid of bricks in this case. So why don't we go ahead and open that example up so we can take a look at it. Close all of these, go to Breakout 3 in the repo, and then we'll go ahead and run it. So largely still the same. In fact, this will always stay looking this way throughout the rest of the course. But if I hit start, we'll see that we started with just a single row at the very top of bricks. And in fact, we also can see that we have collision working and breaking the bricks. It's not functioning in the way that we might expect it to, and we will take care of that shortly. But we do indeed have bricks that are in play and are being taken out of play when the ball collides with them. And we still have infinite sort of the ball going below the surface. So if that ever happens, we're kind of out of luck and we have to restart the game. If I restart, just rerun this one more time, we'll see that it's actually a little bit smaller. The ball is moving a little bit faster as well. So we're randomizing a few things for this example. I'm going to run it one more time. I'm going to try to get a group of more than one row. Let's see if we can get that. This should be generating between 1 and 5. So there's 2, for example, 2 rows. And the rows have variable columns. With this resolution, we can fit 13 columns of these 32 pixel bricks with 16 pixels of padding left over. Those are the sort of the restrictions that we have with this virtual resolution. Recall, we are using a virtual resolution. In fact, the same virtual resolution that we've been using, 432 by 243. But with a little bit of just a few variables, we already sort of have this dynamic play field. We have not just one row always, although we did get that just one row several times back to back, but between 1 and 5 or so. Let's see one more time if we get multiple. So here we have 4, and if we just let the ball, something kind of fascinating about watching the ball just sort of having like God mode on in Breakout or something where your ball just doesn't bounce off of bricks. But as you can see, they're sort of there. They're hovering in space. The ones that were collided with are in play. The ones that the ones that were collided with are out of play. The ones that didn't get collided with are still in play. And once we finally break every single one, we can start to think about, okay, well, let's go to the next level. Maybe we'll start to add more color variety, maybe higher tiered bricks, so on and so forth. So if I go over to Breakout 3, if we look in main, the play state ultimately is going to be still the state we're going to look at, but we did add another frame table for our bricks, so generate quads bricks. Now, bricks are relatively deterministically generatable. They're all the same, or rather the quads are deterministically generatable because they're all the same width and height. If we look at our texture again, which if we pull this up, we'll see that the bricks at the very top of the screen are kind of all in these 32 by 16 squares, kind of going left to right, top to bottom, about 4 rows worth. We could just iterate over essentially those 4 rows, and then minus the balls, the heart, and the last sort of key is kind of in a weird spot. We could, if we won't use that in this particular lecture, but if folks wanted to use that, they could define a quad themselves by figuring out, okay, what's 5 times 32 on the x over, and then 3 times 16 down, get a 32 by 16 rectangle and get it that way. But if we assume that we want these sort of 6 by 3, so 18 plus 3, 21 bricks or so, we could just iterate throughout the table, offsetting down as needed to get our 21 bricks and generate quads from that. So let's go ahead and look at that function really quickly, and we'll just skim over it. Folks can read it, the implementation if they want to at home. But if we say, so here we are taking a slice of, in fact, this is a helper function that we've written to, Lua doesn't have a function to do this by default, but we do have this larger generate quads function, which takes an atlas and gives us the width, and we give it the width and the height that we want to assume that every sort of image within that texture is, and then it will just do the job of automatically splicing the whole thing for us top to bottom in these x by y increments, in this case 32 by 16 increments. And so if we go ahead, and in this case you can see table.slice is just whatever the result of that is, which will be a table. I want from index 1 until index 21, which I just alluded to, 21 different bricks. I just want those 21 bricks. If we were to just, in this case, you can look at this table.slice implementation. All it does is just create a new table. It's not an in-place slice. It'll actually return a new slice of the table. So we will iterate. This is Lua's iteration loop syntax, which we might not have taken a look at for its actual iteration, numerical iteration. But if we say that the function takes in a table at first, a last, and then a step value, we can say, okay, for I gets first or 1, so in the event that we didn't actually pass it a first value. So start I at 1, or whatever we define as first, up until last, which this comma is, or the length of table. This is Lua's way to get the length of a table with this hash sign here. And then this an additional comment here is the step that we should take when we do our iterations. We could give whatever step we wanted to. We could give every 2, every 3. We could do -1 if we wanted to iterate backwards through a table. We could say I gets the length of table until 0 or until 1, do a step of -1. And then we're just going to say at sliced, at the index of slice plus 1, we're going to just get whatever table at I is. And then we're going to return that. So slice is essentially that 1 through 21 in our particular use cases window into that table, and then just uses this larger generate quads function, which we're defining and including with the repo. Takes an atlas, a width, and a height of whatever tile. This is assuming a uniform width and height that you want. We're going to decide what's the width and the height. In this case, this is the number of images in the sheet, so the number of sprites wide by tall. We just have a number that we're going to start with, and then for this is a nested loop here, so we're going to, on the y-axis, we're going to iterate in rows, but through each row we're going to take whatever the column is at that index. So for x is equal to 0 within that loop every time, we will then go the width of the sheet over in those blocks, because it'll be calculated based on the width and the height. We'll just generate a new quad. So for every y, we're going to grab a tile's width, or an image's width, all the way until the end of the x-axis, the size, the number of sprites in that sheet on that axis. Then we're going to loop back down to the next y value, start x again at 0, go over, go again, y is now the third one down, go over until we've gone all the way down through the sprite sheet, and we've grabbed the x and the y's width of the image that we care about. In this case, we care about the bricks, 32 by 16. So we're sort of pretending that the sprite is comprised of 32 by 16 bricks. If we open the graphic up really quickly, we're sort of pretending that this whole thing is just bricks. We're splicing it up into quads. We'll iterate down the line y all the way down to whatever that would be, this tile sheet divided by 16 y, and then the tile sheet divided by 32 on the x, and then these 21 bricks here. And that's how we can divide. And this is a common thing that you'll see when you typically have a sprite sheet, for example, a texture sheet that you might use in something like Minecraft, you might see that floating around on the internet, or lots of games where you might have an animation, a set of frames that are the same size. For example, a character might not really change its size, even though the animation looks like it's changing a lot. In that instance, you would do what we just showed with the generate quads that takes assumes a uniform size of everything in your sprite sheet, and then just that's your one sprite sheet. That's your one sort of table of quads. In this case, things are a little bit more dynamic and all packed together. So we're pretending, but we're just going to slice the first 21 off of that ultimately fully chopped up sprite sheet. And so if we assume all of that, we have our generate quads, all of those utility functions. We won't have to look at those anymore throughout the rest of this lecture. But for folks who want to create their own and for future animation-related things, that'll be helpful. If we go back to main.lua, that's where we were just looking at. So that's where we create the actual bricks table. We now have all of our bricks. We can go over to our play state. And whoops, I didn't mean to press that key. We'll look at here inside of our init function, if we look up here, is where we're going to actually create our grid of tiles, or grid of bricks rather. And this is really important because this will tie into the later examples where we begin to, in this particular example, we just have a very plain sort of collection of just one blue variant brick. The actual columns and rows were random, but the texture was the same. But let's say we wanted to add variants of the skin or the tier, or we wanted to maybe add gaps, or maybe we want pyramids, or we want inverted pyramids, or whatever you can think of sort of visually. Well, all of that functionality is best, I think, encapsulated in sort of an object, sort of how we decided last week to encapsulate the behavior of what it means to have a state, a game state. I think it makes sense to encapsulate the idea of generating a level into this thing that we've created called level maker. As we see, self.bricks, right, in init is just getting level maker.create map. And so before we take a look at that, we'll just quickly see we have in here, again, all the same functions we saw previously of update and render. We have the paddle and the ball being updated in here with DT. And then we have our collision detection. We have, and that's for the ball and the paddle, but then we have for k brick in pairs, recall that's how we iterate over a table. Self.bricks, which is that group of bricks that we're going to get from level maker. If the brick is in play and our ball collides with that brick, we want to call this function hit, which right now all it really does is just essentially disable in play so that it no longer renders, which if we see in here, every time we have actually it's deferred to the render function, the render method on the brick class itself, but we're calling render on every brick. And if we look at brick, which is a new class that we're defining here, a very simple class, we have self.inplay, which starts off, we have self.inplay in the hit method, which will turn false if we hit. And so the purpose of that is that now we can essentially mask out the bricks that we don't care to look at or collide with. We can just essentially do an if statement to ignore that brick for the purpose of collision and for the purpose of rendering. And sometimes you want to even preserve this if, for example, you were to, let's say your instinct might be to just completely get rid of the bricks. And that might work fine, although you would potentially run into issues. You definitely want to remove it in place when you're doing iterations. But let's say potentially if you were to lose or some other condition in the game, you wanted to show the same exact map to the user or to the player rather than have all of the bricks stay exactly as they were. Well, it would be harder to do that if you were getting rid of the bricks. It's much easier to just toggle all of them back in play and then restart the level that way. So this is an option. You certainly could remove the bricks, but we're deciding to do this in case you wanted to consider doing that and just to illustrate it as an option. And then again, we saw this same logic when we rendered the paddle. We have our own bricks quad, and then we're essentially doing a calculation. We're starting at 1, we're adding our color times 4. So the color is essentially which group of bricks, it's every 4 bricks in this case, essentially that's where the colors are divided up. And then we're also going to add our tier. So that's an index into sort of that group of 4 colors. And so that's going to allow us to take our tier and our color, combine them, index into those 21 bricks that we saw, 21 bricks that we saw, and then that will give us the exact rectangle that we want to display on the screen. And these colors and tiers and whatnot will be a lot more relevant as we start to explore later examples in here. And so lastly, the last piece of this, again, which I alluded to previously, is the level maker. And so the level maker is going to start off slightly simple, but we're going to just create in this case, a static function. So this isn't a method of level maker. We're just going to create a static function because we don't really need this. We don't need a level maker instance per se living anywhere. We can just call this function that exists somewhere in this level maker class and sort of encapsulate the idea of it, but not worry about creating a level maker object and having it call a method and preserving state. We don't need to really worry about too much of that right now. And this is a common thing you might see for classes that have this function you might use as a utility or something, and you want to keep it around but not create an object of a level maker that exists in memory. But essentially here we create a random number of rows and columns, which is what we saw previously, between 5 rows and between 7 and 13 columns. Remember, 13 is the max number that we can visibly fit on the screen, so we're just going to cap it at that. And then again, another 2D loop. So for y gets 1 until the number of rows, so we're going to iterate through our rows, and then we're going to do a nested loop to iterate from our x's going left to right. For the number of columns, we're going to say b gets a new brick. This is the constructor again. We're going to say it starts at x minus 1, and then it's going to be multiplied by 32. Remember, coordinates, even though Lua is traditionally 1 index, which is what we're doing here, you could start this at 0, but typically in the world of Lua and Love programming, you start your loops at 1. So we're just conventionally doing that. But you're going to want to minus that by 1 before you do your multiplication, because coordinates are not 1 indexed, they're 0 indexed. So assuming that we want to start at index 0 for our x-axis, we're going to subtract x by 1, multiply by 32, add 8 to give us some minimal padding from the left side for all of the bricks. And then we're going to add also an offset based on the number of columns, the delta between the number of columns and 13, multiplied by 16 pixels, which is, again, the max number of bricks that we can store on our map, on our size, or on our screen size. And so this just ensures that whatever x we're at, we're shifted over a certain amount by padding if we don't fill those 13 columns. If we have 6 bricks, for example, this would end up being 13 minus 6, which would be 7, times 16, which would be the amount of padding we would have on the left edge of the screen, which would just make sure that everything is centered, which it'll put us about halfway between the two edges because the bricks are 32 pixels wide. So by dividing by 2 and having it be 16, that makes sure that we account for the right edge of the padding implicitly by shifting over by 16 pixels instead of 32 pixels. And then lastly, a y-coordinate, we're just going straight down in 16. They're not nothing too fancy. They're 16 pixels tall, so this just ensures that they are all contiguous. And then lastly, we're inserting that into our bricks table and then returning that, which again is what we were using previously in our play state. And then now we have all the bricks in our actual play state. We can collide with them, set them in play, out of play when we do hit, and everything works as intended. Just one more reminder just to illustrate. We can visualize it. Again, you see the rows and columns. You see that we can basically approximately fit. This isn't fully getting us 13, but you can kind of assume that there are about 13 bricks worth of space. We have padding, it's centered, and that's again accounting for the offset between the number of columns and the number of bricks we actually created in our table. It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we were to put 3 more, we would have just a little bit of padding on the left and the right, but that's how much we can fit. And so they're all just being rendered and set in play whenever the ball hits them, and that's the extent of essentially the level maker, the foundation of all of our future procedural grids throughout the rest of these examples, which will be a lot more concise, I think. OK. Water break.
Good.
A lot of words. So that was essentially getting Breakout in a visual state that is more or less what we expect to see when we look at the game. However, there's one sort of major thing sticking out, and that's the fact that when we were just playing the game, the ball was sort of going right through the bricks and not really functioning the way that it's intended to. So this will be a larger example in a couple of ways, but this is the collision update. And so unlike Pong, unlike Flappy Bird, there needs to be a certain way that the ball behaves depending on which direction, for example, and how much the ball clips into the bricks, because it can bounce into the left and the right edges of the bricks, as we probably saw, the top and the bottom. Pong was very simple in that the ball would move left to right, and then it would always essentially be checking to see if it bounced against the right edge of the left paddle and left edge of the right paddle, and then it would just bounce inwards. But if it bounces off of, for example, this edge here and it's going this direction, we want it to bounce out this way. But if it hits this brick coming from the bottom, we want it to go this way, and so on and so forth throughout all four directions. And so collision ends up actually getting a little bit more complicated in this example than it does in Pong. And also similarly, the paddle here, we didn't do a whole lot of fancy work with Pong's physics when we did Pong, but in this particular example, if we want to, and also in real Pong and Breakout, if we want to give the paddle just a little bit of physical control and have sort of an influence on the angle, we need to also take a look at how to collide, how to test for a particular collision on the paddle in a slightly different way than we previously were doing. And so we'll start by just talking very briefly about the paddle collision, because this is the simpler aspect of the two, the simpler process of the two. And that's essentially that there is an offset that we could look at. When we think of the ball coming down and hitting the paddle, essentially it's going to hit the paddle anywhere along this top edge. And depending on which offset it hits, we could sort of, if we sort of eyeball how Pong and Breakout worked, the sort of closer to the edge it hits, the sort of faster we think it should bounce and sort of like sharply bounce. That's sort of the feeling that one gets when playing Pong or Breakout. And so in order for that to be calculated, we have to say, okay, well, how far from the center of the paddle did the ball actually collide? So if the ball hits, and we can call that ball offset for all intents and purposes right here, but if the ball were to hit, like say right here, the offset is going to be smaller. It's going to be maybe 2 or 3 pixels. But if the ball were to hit somewhere over here, well, now we have a much larger offset. And also in our example, we're concerned with, is the paddle moving left versus right? For example, if we move the paddle to the left, but the ball just continues to bounce up and to the right as it would normally do, well, that's not exactly what we expect. We might expect, as we're moving the paddle, for that to sort of have an effect on the ball. So if we're moving this way, we sort of want the ball to go bounce this way, especially if it's right on the edge. That's kind of where the sweet spot is. And so we can essentially figure out what the midpoint is of the paddle and the offset of the ball, and then just multiply. If we're assuming we're moving in this direction and we do that calculation, we'll just multiply the delta between the ball and the paddle center and some constant that we can tweak, and then change the dx of the ball to be negative in that case, and then vice versa. If the ball were to come here, for example, and we want to make it go sharply to the right based on how far away it is from the center, well, we'll take this offset here again, and then we'll just go ahead and convert it to a positive dx in the same exact way, the farther away the ball is from the center. And then we'll take a look at brick collision as well. But before we even get into brick collision, let's just look at the code and where that is before we make that transition. I'm going to go ahead and also take this opportunity to demo this example so we can see visually what I'm talking about when I talk about this. I'm going to go ahead and close all of these. Lots of projects open here. OK, Breakout 4. And I'm going to go ahead and run this. So the ball's moving at kind of a relatively shallow angle, but I'm going to go ahead. Notice that it bounced. It didn't actually just collide through it, but it's behaving a lot more like we expect the game to behave. And so, whoa, it's a little bit too sharp on the angle. But you saw that I moved the paddle to the left and hit it kind of right on the edge, and it really took a sharper angle turn to the left and allowed me to sort of influence the trajectory, the angle, in just the way that I cared about. And not only that, but we're sort of getting ahead of ourselves a little bit, but the ball is actually colliding with the bricks and not just sort of clipping through them as if it had unlimited power or whatnot. I'm going to just run it one more time and see if I can illustrate that, bouncing maybe to the right or the like. I was hoping for also slightly more bricks, but thankfully it's moving just where I want it to. So I'm going to move to the right and hit it real hard, and then it's going to give a nice sharp angle bouncing to the right. Let's see if I can get it to the left. And there, I hit it slightly not on the edge, and I was still moving to the left, and it still hit it and moved it to the left, but it was a little bit less sharp of an angle because it was kind of towards the center. And that's sort of like the overall feel that we're going for, because that's kind of more or less what Pong and Breakout were doing with their own physics. If we go ahead and look at the play state, which is going to be in source, states, play state. Now, we're going to find, we got a lot of collision code in here, but essentially the code we just looked at needs to take place, of course, in the paddle versus the ball collision code, like where the ball is colliding with the paddle. So we're going to go ahead and, again, we care about whether the paddle is actually moving to affect this. If the paddle is not moving in a particular direction, it's just going to kind of preserve its dx and is going to just shift its dy. But if we're actually moving left, which we can determine by our dx being less than 0, which would be moving to, our paddle's moving to the left, or moving to the right, we can now use those and then do a check. So the center is also going to be an important thing here, because recall, we need that offset. We need to actually have an offset from the center of the paddle to wherever the ball hits the paddle to determine, assuming that we're moving either left or right, how much we should essentially multiply. We should essentially multiply some constant by that amount to add onto our dx to make it sharper. Because the more our dx is relative to our dy, the sort of sharper the angle is going to be. If our dx is relatively shallow, it's not moving a lot, we'll have a much more upward trajectory, because our y velocity is higher, is taking more precedent than our x velocity. But assuming our x is really high, it's going to be more like this, and it's going to be a lot sharper. So we're going to go ahead and take a look at some of these other variables here. Starting bounce dx is our what we want our dx to start at, like our initial, like, okay, 50 is the assumption that we're going to work with. And then a multiplier. These are tweakable. You could make starting bounce dx higher or lower, depending on your tastes. But these are sort of numbers that I've experimented with and found work pretty well for demonstration. And then you can do some math here. If self.ball.x is less than the center, so if we're moving left, this is the other condition here. So if the ball is to the left of center of the paddle and we're moving left, so again, that's kind of, you can kind of see that on our slide there. It's exact, actually, kind of example I'm talking about. But let's assume that paddle's moving left and the ball is to the left of center. Well, that offset there, we can just multiply that by that 8 magic number that I've come up with through balancing. And then we're going to add that 8 times offset to 50. And then we're just going to set that to be our negative dx. And so if we look at our code, we'll see that happening here. So the offset is the center minus the ball's x. And then we just set that to the negative starting bounce dx. And then we do also an additional minus of the angle multiplier of 8 times that offset. And we do the exact same thing on the right side, only it's positive, because if we're moving to the right, or to the right from the camera's perspective, the offset is going to be on the right side of the paddle if we want it to move to the right. And then it just needs to be, the ball is going to want to bounce to the right in the case that we're moving right. And so it needs a positive dx. And so we're going to multiply accordingly in the same way, just positive instead of negative, but taking the same offset, sort of taking wherever the ball's x is minus minus the center of the paddle. And so that's essentially what we can do to give it this sort of feeling of a physical paddle. It's not exactly modeled in the way that Pong or Breakout would have modeled theirs. I believe theirs was more intricate and it was also electrical wiring, or it was actual electronics that were wired together to perform the logic. But ultimately, it feels really good. It feels similar to it, and it's good enough for our example. That's the paddle and the ball, giving it sort of, I guess English would be the term, putting some English on the ball or whatnot, whatever folks say in that circumstance. So the other bit of code we're going to need to take a look at is, if I go transition to the slides, the brick collision. Now this is a bit more complicated, but essentially in Pong, when we were detecting the ball colliding with the paddle and then bouncing back. Essentially what we're doing now with our current paddle. There's an AABB collision detection process that takes place. And then for the paddles, it was sort of hard set. Okay, it bounces from if you're player 1 and your ball comes down, you want it to bounce to the right. And then same thing for player 2. You want it to bounce to the left. It's just a simple inversion of your DX, essentially. But with Breakout, if you come in on the top, you're going to want it to bounce up. But if you come from here and you hit here as well, on this edge, on X edge or a Y edge, you're going to want it to bounce in a different direction. You're going to want to flip whether it's your X or your Y velocity. It's not just a simple always assumed to be change your X velocity in the case of Pong or Y velocity in the case of Breakout. So we can start by thinking of this in terms of midpoints. So we've been doing AABB collision detection, which just takes a couple of boxes, their XY coordinates at the top left, and then just does some simple checks to make sure there's no gaps between them. But we're going to want to actually figure out at the moment of collision between these two, there's going to be a smaller and a larger gap between either axis, the X and the Y axis. So we'll say that we have these center points, CXB and CYB, and we'll use capital B for brick, lowercase b for the ball. And then I will posit that we can then take an offset called OX that is essentially just the brick's sort of center point on X minus the ball's center point on X. And this is an illustration just to kind of show what that looks like. If we have center points here, the brick minus the ball, in this case, this will be a positive OX. And if it were here, rather on the next slide, if the ball were to the right of the brick, then it would be a negative OX. So this is a signed value, and this is relevant because this will allow us to correct the ball when it collides, which we have to do in order to reset it. If the ball were to hit, for example, here on this left side, we want to make sure we shift it back out towards the left. And if it hits on the right side, we want to shift it back out towards the right. And the same idea applies to our Y-axis. We can take an offset of Y. So how far apart are the midpoints between the brick and the ball on the Y-axis? And this can be negative as well. And we'll use this negative value to correct for the ball's collision based on whether it hits the top or the bottom. Now, if we pretend that we are calculating a collision that is approximately at these two values, but let's say the ball is coming down and it hits this brick at 10.5 and 10.17. Now we can see that they are 12 pixels apart on the y-axis, but 0 pixels apart on the x-axis. So they are essentially almost completely aligned, but there is a delta between the two on the y, and that's where we know that the collision is actually taking place. We can intuitively see that. It's not occurring on the left or the right side, it's occurring on the top side. So we have OX of 0, OY of 12. Those are the offsets. And just as a spoiler alert, essentially the offset here is almost always just going to be, or the axis is always going to be the larger of the offsets typically. But there's some math we're going to have to do to actually shift, to actually figure out how much we need to shift the ball by when we resolve the collision. So assuming an OX offset of 0 and a Y offset of 12 here, oops, sorry, didn't mean to touch the TV like that. There's going to need to be these other values called PX and PY, which are the sort of penetration depths of X and Y into the brick from the ball's perspective. And we can just calculate that math here. So there's a couple of these values, these numerical values, that are essentially half extents or radii, but in the case of the paddle, it doesn't really quite have a radius so much as it has a, because it's not symmetrical, it's going to have a difference in its width versus its height in terms of sort of the effective analogy for the ball's radius. But we essentially need to calculate, between the two, like there's a minimum distance that they have to be at in order to have a collision, or rather a maximum distance they're going to be at in order for a collision to resolve. In this case, they're literally touching. If we assume the ball is 8 pixels large, so it's a 4 pixel radius, and this is a 16 pixel tall brick, then this sort of, I would call it a half extent sum, HX you could think of it as, but it's essentially this math here. This is going to be the 12 pixels, it maps up here exactly to 12 pixels, but essentially there's going to be 12 pixels at the very least between the two minimally. And if, depending on how big the collision is, that delta would be a little bit smaller, perhaps. But we're essentially going to need to shift backwards that amount on whichever ball or whichever axis got collided on in order to bounce the ball outside of the collision. So we'll just resolve this math here. We can see that, and that's what the ABS of OX is. That's going to be just the amount of pixels at which the delta in these two exists at. So there are 12 pixels apart here. That's the offset Y. We're going to want to essentially take the max distance between them, subtract that, and then that's going to be the amount that we end up reverting the ball by when we resolve the collision. So let's go ahead and just shrink that math down to recall. It's just essentially the radius and a half width and height of the paddle. So that ends up amounting to this math here, 16 plus 4 minus the absolute value, ABS of OX. So OX in this case is 0. They're literally aligned on the X coordinate here. So that's going to amount to 0 here, and then 12 here for the Y axis because they are 12 pixels apart. So we end up with PX, so a penetration depth of 20, and then a penetration depth of 0 on the y-axis. Now, between the two, this one is higher, 20 pixels higher, and this one is lower, 0. And we actually want the lower of the two because that's going to be the one that we just triggered the collision on. So folks might see the 20 and be like, okay, well, that's higher. Maybe we should have the collision take place on the higher value. But in fact, it's higher because from the perspective of the algorithm, it is effectively penetrated in 20 pixels because if we assumed that this was a collision of some kind here, then it would actually be 20 pixels in. But that's not the collision that happened. This is the collision that happened. And so we could essentially move this ball around and these values would all change. But as you run these numbers, the lower of these numbers is always going to be the most recent definite trigger point, the actual collision that occurred versus the axes that are closest apart at the time of collision by virtue of just the way that the rectangles are sized and the way that midpoints work. So you're going to end up ultimately having a y-axis collision with the lower of those two px and py values, which then we can decide to shift the ball negative based on that, the amount that they collided, the amount that they were different. In this case, it's going to shift it by 0 because that's what we actually ended up with here, 0 pixels. But if this were actually clipped in, this would be slightly higher. This would be like 1 pixel or 2 pixels or the like. But in this case, it's going to be 0 because they're literally touching for the sake of illustration, just so you could see them looking at each other. Or it'd be like 0.1 or 0.2 or something like that. And so if we just run this same math here, it's the exact same thing. You have a collision on the right side. In this case, it's going to be x is ahead of the paddle. So we have 54 there, 34 here. It ends up being about 16 plus 4 pixels, 20 pixels of difference between the two at their max distance, their minimum max distance for collision. So that's what's shown here. OX is negative 20, Y is 0. And so we condense the same math that we did previously, and it's the absolute value that we're taking of the offset on the x. So it's minus 20 here. We end up with a 0 value on the x-axis, and then a positive value on the y-axis, even though, again, they're at the same y level, but the x-axis is what they collided on because that's got the less delta on it than the lower delta on it than the other axis. So we have 20 pixels of penetration depth or of delta there effectively, but the 12 pixels here is essentially showing what it would think it was triggering if it were coming from the top or the bottom. It would think that it was a 12 pixel penetration into the rectangle, but it's actually not the collision we're checking for. We're checking for the lower of the two. And so we have a x-axis collision, and then we shift it negative by px, the ball actually. And then that's essentially the gist of it. It's a little bit convoluted, but we'll take a look at it in the code here. Or it's seemingly convoluted. It's I think, intuitive to a certain extent, but we just have to essentially think about it in terms of if two things were going to collide together, of the two axes that we are looking at, which is going to be more likely to be further away from the other? And it typically is, unless you're at the corners, which is where they can be about the same. But if you're on a flat surface relatively toward the center, it's always going to be the opposite angle, the opposite axis that you're close to, that is the colliding axis. And then depending on whether it's a positive or negative offset, which recall we have the OX being negative or positive, OY being negative or positive, we can use the fact that it's negative or positive to determine, okay, we have to actually set the or we have to actually shift the pixel by, or shift the ball by X pixels and then change its dy accordingly. So let's go ahead and go into play state. It's going to be below where we collide with our, oh sorry, this is actually the code here. I scrolled down in advance. But so this was where we collided with the paddle. We checked the paddle collision code. We scroll down a little bit here. We're going to iterate over all of our bricks as we were doing before. And then we're going to here to essentially do all the math that we just showcased visually. We're going to create our half radius points or our half extent points, our CXB, our CXB lowercase, and those were the center points for our ball and paddle, respectively. We calculate the offset just by multiplying those center points, or sorry, by subtracting the ball's center point from the paddle's center point. We're going to get the offset. It'll be negative or positive, which will be useful when we determine how to resolve collisions. And then we perform that calculation that I showed on screen, which is the px. We're going to take the absolute value of that offset, and then we're going to subtract it from the sort of half point, the half extent sum of the two colliding entities. And so we want the lower of the two, not the higher of the two. And when we do that, so if px is less than py, we can set the dx negatively. So in the case that the penetration depth of x is less than py, that means that we collided on the left or the right side. So we therefore should reverse the dx, whatever that was. If it was coming from the right side, we want to shift it back to the left. And if it's coming from the right side or left side, we want to shift it to the right or backwards. And then we're going to want to also take the negative px or px from our ox, our offset. So if it was positive or negative, we're going to want to shift by whatever that amount was, depending on which side of effectively the brick that we collided on. That'll nudge us just out, if that px was 1, that means we went in 1 pixel. We want to shift back out 1 pixel. Same thing for the top and bottom. And the same logic is just applied here. And then the last ingredient to this is that typically with games like this, we did this slightly with Pong, we want to also ensure that things kind of keep moving and escalating in a sense. So we're going to just add a multiplier to our acceleration on dy, which is sort of the more meaningful axis. You could do it on dx as well, but dx, because you manipulate dx through paddle movement, that doesn't feel like a great, and it also kind of goes back and forth. It doesn't feel like a good use of balance to manipulate dx. dy, we can just multiply that, so the top to bottom interactions will be faster, which will make other interactions feel faster. And then eventually the game should, in theory, be so hard to play, we probably would want to cap this, and we do in later examples, but it'll be too hard to play that you eventually will probably lose, and then that will be game over. So just as a reminder, we just play it one more time. That's effectively all of the collision code. I'm just going to go ahead and do another example here. You can see it's coming from the bottom. It bounces towards the bottom. It got shifted. I'll do this. Maybe we can get a few more bounces this time, if we're lucky, and it'll be fun. Okay, in that particular instance, it bounced so quick off a whole bunch of them that it just cleared out a whole bunch back to back. But essentially, that's the gist of what's going on. And so now we have a way to determine, okay, something collides from the left or the right, or the top or the bottom. It's just based on that offset delta between the two axes. And we want to essentially assume that the axis with the lesser of the two deltas actually is or penetration depths is the actual one that collided. Because the higher penetration depth, it sort of implies whatever is closer on the axis, which if you're on the top and you're right in the center, it'll be x. And if you're on the right and sort of centered, it'll be y. And so on those exact angles, you want the lesser of the two penetration depths. Which on the top example, it will be x. And if it's on the side, it'll be, if you're on the top, it'll be y. And if you're on the side, it's going to be x. OK, so that was probably the most intricate, complicated part of today's lecture. Thankfully, I think the rest of the examples should all be relatively tame if we take a look at the next one. So yeah, indeed, the next example is going to be quite a bit simpler. OK. So now time to transition to something a little bit more sort of playful. We currently have a bunch of bricks, but no real way to determine, okay, what's our loss condition? I mean, there's sort of a soft loss condition with the fact that the ball can infinitely go past the bottom of the screen, but that's not ultimately what I think is the most ideal way to approach this game. So what I'm going to go ahead and do is go over to Breakout 5. I'm going to go first and close out all these examples. And then if we go ahead down to Breakout 5, I'll just run it real quick to showcase what we're going to add here. So same as usual. Now notice at the very top right, so a couple of things going on here. One is that previously when we hit enter, we would just start going, and now we can actually serve the ball. Notice also fun sort of thing that the ball follows the paddle, which is how typically games like this, Arkanoid or Breakout or whatnot, will often have this. But we have a few hearts at the top right of the screen. So hearts are like a very Zelda, I think people usually think of like Zelda or games like that, a very sort of video gamey thing. We also have a score that we've added there too. So I'm going to go ahead and press enter to serve. It's going to start moving in a random direction with the collision detection we just added. And then I just try to add a little bit of extra velocity there. So every brick is worth 10 points in this case, in this particular tier. And as we'll see later, future colors will add more sort of different types of score intervals or score amounts per brick. But when I took a hit, you notice that I did detract one of my hearts, and I have 2 out of 3 hearts. So I'm going to press enter to serve again. If I move around, hopefully I'll purposefully just lose for the sake of time here. But one more time. And notice the ball is also randomly being set to a different color just for fun, because we have multiple textures, multiple skins. But we essentially got all 3 of our hearts detracted, and then now we have our game over state. And it says final score 70, so the score was passed from the play state over to our game over state. And also, the bricks and everything actually really were transported between the play state and the serve state as well. So we can take a look at that here in just a second. Now, a lot of these things folks have seen before, so we won't spend too much time dwelling on particulars. But if we go over to the serve state, for example, we'll see that we have ultimately some tracking logic in place here for the X of the ball to follow the paddle and just be raised above it. But also, every time we called state machine change, remember, that was how we can essentially do that handshake between states. We talked about that at the end of last lecture. But every time we call G state machine change, recall, it will call its own exit function if defined, and then it will call its enter function if also defined. And so what that lets us do is bring data from one state into another state. Because remember, every time we create a new state with that state machine in main.lua, it's going to create a brand new copy of that state, just this brand new object. And that's often what we want, but often also not what we want, depending on whether the states should preserve some amount of continuity between them. In this case, if we're in the serve and the actual play state, we can notice, if I run it again, this state, the title state or the start state, has really no state that's meaningful that we need to preserve, but this serve state here has a score. It has our HP. That's another variable that needs to move around. It has the bricks, because every time we create a brand new play state, this is all just right now what you're seeing is it creating everything from scratch. But as soon as I go into this play state, like, it didn't really look like much changed, but in fact, some stuff did change. We went into a whole new state. We're in the serve state. We are now in the play state. And so, well, now we're in the serve state again. But everything is being handed across with that G state machine change, and we're taking those values in and essentially taking charge of those as our own new state when we do the enter function of all these. For example, the enter between the start state, between the serve state and the play state. So I'm going to go ahead and close that out. We'll take a look at the serve state. Change is going to play, so we're going to go to the play state, right? And these are all of the variables we want to pass from our serve state to the play state to say, hey, you now take charge of these variables. These will be your variables to handle. We are going to essentially get deallocated. The state's going to be lost. But before we do that, here, take these things, take charge of them. You need access to this information to preserve that continuity. So when we go to the play state, and if we go up just a little bit here, notice that we're defining this enter function, which we saw previously. It takes in a params table, and we're just taking all of those params, the table that we just saw, and we're just going to assign them to self dot the same thing. So self.paddle equals params.paddle, so on and so forth. We're inheriting those and we're saving them as if now they're our state, which they do become our state. And so now, in the same exact way, if we were to go, so for example, to the serve state down here, if we actually go below the height of the screen with the ball, we can do the same thing here. So if self.health is 0, so we're now storing health, and so we're subtracting 1 from health, and that's mapping to our hearts. We have 3 HP to start with. 1, 2, 3, you're out of the game. If health is 0, we want to change to game over. So that's, remember, we did see that. It's a new state. Or we'll change to the serve state. And again, we're passing in the things that we care about as being preserved between the two. We care about the paddle. We want the paddle, its position, its texture, all those things. We want the bricks. We want the health. And we want the score. Everything else, really isn't much else, but those are the things that we want to preserve between the two that we communicate back and forth with. And so if we're in the play state, for example, you'll notice that we have render score and render health as a couple of functions we're defining in main. So if I go over to here, and I'll just quickly glance over them. We won't talk about them too much. But there are a couple of helper functions. The reason that we're defining them in main is because they're going to be drawn in several different places. Rather than define them in every state and just having them repeat over and over again, it sort of makes sense to have them defined here in main. Or you could create a base state that has access to that function and then do the inheritance thing we showed last week where you do includes equals that base state. You could do that as well. Here we're just defining a function in main, which just takes in a health, and we'll just render it onto the screen using love.graphics.draw. Just with the hearts, we have this new we have a texture and hearts that we're dividing up, and we're giving to that function to call and render. So if essentially we're drawing from 1 up to our health number of times a red heart, and then for the rest we'll draw frames 2, which is a dark heart. And so if I go ahead and open up the hearts texture, might have just spliced this out from the I think I just spliced this out from the full texture. It's a little bit hard to see here, but it's just two sprites, just two like 8 by 8-ish sprites of a red heart and a unfilled heart. And we just draw, if you have 3 HP, draw 3 red hearts. If you have 2 HP, draw 2 red hearts and then 1 gray heart. If you have 1 HP, draw 1 red heart and then 2 gray hearts. And that's essentially what we're doing here. From 1 to health, draw those red hearts, and then from 1 to 3 minus health, do the exact same thing. And then we have the display FPS and also a display score, which takes a score, and it's just a couple of very simple function calls that just set the font to small, and then we'll just render our score up to the top right. So that was the hearts update, Breakout 5. Now Breakout 6 is kind of fun. So this is called the Pretty Colors update, just for fun. This is just a funny, goofy title. But as you can see, currently we've only been dealing with very boring brick layouts in the sense that we just have blue bricks and they're just worth 10 points. Nothing really too amazing about that. But if people are familiar with Breakout, even as we saw, as you can see here, but even as we saw in the example that CS50 originally did, CS50 proper, there's various colored bricks, and they all mean different things depending on the game. They can be a higher tier. They can take a certain number of times to break. They can break and then go down a color and then go down a tier and then be worth more points accordingly. And so they essentially act as a way to, 1, vary the visual aspect of the game, but also 2, provide difficulty and some dynamism. And it's just fun. I think it just looks really cool. So this is all done in Level Maker, which we saw previously. So we'll just go ahead and transition over to Level Maker in Breakout 6. We won't spend too much time looking at this because it's essentially the same logic, in that you have rows and columns of bricks being generated in a table that have their own XY coordinates. But the only other difference is now we're deciding, okay, should we also just change the skin and index into, we have the 21 bricks, like we'll just do some math, index into, whatever our skin is, and then add an offset or that'll be for the tier, and then that will represent what that brick actually is worth. And then there's some logic that we can use to calculate points and whatnot. So we'll go over to, in this, first off, let's test it. Let's just actually have it run. I'm going to close others from here. And then let's go ahead and run this. So right out the gate, we can see a lot more visually interesting. We've got purples and reds and greens. These will all still, I think, potentially be single hits, and they're all still worth 10 points. We haven't really done anything to change how they function, but they visually are really cool looking. I'm not even touching the screen. I'm still somehow not losing. Yep, we're still going. But essentially, just with just a few patterns here, we have some pretty interesting variety. Now we can see just at the very top row, for example, you've alternating colors. You've got red, green, red, green, red, green. So just imagine a bit on, off for, you choose two colors and say, okay, if bit is on red, if it's off green, if it's on red, off green, and just alternate between the two. Or you can just choose not to have alternating colors, like the second row, which is purple. Or you can elect to have maybe bricks and then not bricks, bricks, not bricks, right? To have gaps in your bricks, and then that allows you to do the same logic as for colors, except instead of alternating colors, now you're alternating whether there's a brick there as we're iterating through our rows and columns in our level maker. And then essentially this row right below it is doing the exact same thing, it's just inverted. We start off at a sort of off state for should we put a brick there, and then we turn on, off, accordingly. And then if we just run this a few times, we'll see variant grids being generated. So here, notice also, it shrinks to fit it's different sizes that will fit within the screen. This one's cool. It's got green and blue at the bottom and alternating colors. These almost look like they were designed by hand, but they're just using very simple procedural generation techniques. I'm loath to even call it that, but it is sort of procedurally generated grids. And so we see here, again, almost looks like a human made that. It's pretty cool. We'll go ahead and just do it one more time for fun. And this one's actually fully solid, but because we're choosing symmetrical sort of approaches, they're always going to, and also a symmetrical number of columns, or an odd number of columns, they're always going to be pretty nice looking most of the time, especially if we keep it relatively simple. We keep within a grid, we have just alternating colors, alternating spaces, but you could envision a world where you want to do pyramids or inverse pyramids or squares or maybe a circle or something. And the sky's the limit. Ultimately, you just have to write the code, the logic that can speak in rows and columns to do that, and you're encouraged to experiment with that. So I'm going to go ahead now, open up Level Maker so we can take a look at some of the stuff we've added. I won't spend a terrible amount of time covering the specifics, but if we go up here just a little bit, we're doing all the same things we were doing, just having a set of random rows and columns number so that we just have a variable size of our grid. The highest tier and the highest color are essentially just a little bit of math that's going to look at our level and determine, okay, what's the highest, based on the level, what's the highest tier that they can access. If they're at a lower level, we shouldn't give them really high tier bricks. If they're at a higher level, we should make sure that they can potentially do that up to a certain threshold, a certain number, which is that math.min's first argument. No higher than tier 3, no higher than color 5. There are no more colors than that or tiers than that. And so we're going down the line number of rows. We have all these variables for a skip pattern, which is just flipping a coin, 1 and 2, make it true or false. This is the bit flipping on or off. So whether we should have a skip pattern, whether we should have an alternate pattern, what our alternate colors are, should we choose to be alternating colors, what our alternate tiers are, should we alternate tiers, which we can also do, which you'll see if you were at a higher level in the game, in the level maker. And then the skip flag, which is the actual are we on or off when it's generating, and then the alternate flag, are we on red or green if it's doing red and green, or vice versa, to allow you to change sort of how those are generated. And then lastly, we'll take a look down here and then just notice that we have for, if we are generating something, we're going to use this syntax that's particular to Lua that doesn't allow us, Lua doesn't actually have a continue statement, but it does have a form of go to that we can sort of simulate continue with. And that's using labels and a go-to statement, which is from C. And typically go-to is frowned on in the C world because it produces very unreadable code. But in this particular instance, if we just stick to using it like continue, we can sort of almost think of it like we're extending the language in a way with our own syntax. But effectively, we're just saying, OK, we're going to go to a label that I've called continue. And that's if we're skipping, and we should be skipping this brick. We don't want to actually do all of this stuff of generating a brick. We want to just, we're iterating, remember, we're iterating every row and then every brick on that row. So if our goal is to skip bricks, every brick should be off essentially on, let's say, the top row. Well, if we're we need a flag that turns on and off every time it generates a brick. And so if we're on if skip flag is true, essentially, we need to say, OK, we're just not going to add a brick this iteration, but we're still going to keep generating bricks. So let's just essentially skip this loop. Let's continue, but not in the world of C and other languages. That means like keep running this overall loop that we're in, but let's not do the rest of this loop's body. So if we go all the way down here, we can see this fancy syntax with double colons, which is how Lua does label definitions. And these are used specifically for go-to expressions. And so ultimately, all the logic in here is to do all of that. It's to lay bricks, and then depending on whether your alternate flag is set, what's the color that we should draw at? Should we draw, or should we render a brick here, or should we add a brick to the table here or not? And then through this relatively simple set of procedures, even though it looks like it can be kind of a lot, it's ultimately just a set of like check marks or flags that we're holding on to that every time we iterate, and we're just saying, okay, are we in an alternating sort of row? If we are, okay, well, we need an on-off flag, so let's just on-off, on-off, on-off. Next, are we alternating? No. Okay, just put all the bricks. Next, are we alternating? Yes, but let's start off. Let's start off. So it'll be off, on, so on and so forth. And then through those simple procedures, you could think of maybe many, many ways to extend this. You have very interesting dynamic grid layouts. So for folks who want to understand the nitty-gritty about it even more, feel free to take a look at levelmaker.lua, but that is the overall sort of summary of how it's working and how we now have these very nice looking grids. But, and we'll go ahead and just sort of transition back. The other aspect that folks might have noticed, we have these really nice looking grids, but they don't really have any meaningful sort of data associated with them in terms of their score, in terms of their tier, all these things. So let's say we were maybe per at least what the slide is showing, let's say we have green or we have red bricks instead of blue. Well, okay, if a green brick were to get hit, which is what we sort of showcased in the slide there, then let's assume that blue goes to green, goes to red, goes to purple, or the like. So a green brick, when it gets hit, should go backwards in tier. So we're sort of essentially weakening that brick. The green brick is essentially a stronger brick than blue, but by hitting it multiple times, we still get it out of play, and we can even maybe make it worth more points as well, and then also add tiers to these bricks so that not only are they colored in different ways, but maybe they are colored and gold, or colored and silver or bronze. So you weaken the gold to get to silver, to get to bronze, to get to no sort of metallic color. And then that's how you can get even higher tiers and higher difficulties and things like that. So let's go ahead, and I'm going to close all of these. So if we demo that in Breakout 7, I'm going to run this. We'll see here we're starting off with green bricks. So if I just start serving, green turned to blue, and we got 50 points. Okay, another 50 points. See if I can hit a blue to compare the point amounts. Might be tricky for a moment. But this is a lot more akin to what folks might have expected to see. But okay, we actually missed the point total that it gave. It looked like 25 points. But there's also a sound effect now playing too, folks here at home. But 25 points for blue, 50 for green. So there's some amount of math that's going to apply 25 times color, and then probably times tier as well. So we say that purple went to red, right? So kind of this overall idea is just to make the map a little bit more visually interesting, more rewarding, and more challenging. Because if you can imagine all of these were purple bricks, it would take quite a long time to break all of them. Remember, every time we bounce off of the bricks, our Y velocity is going to be increasing. Now we should cap it ideally so that it's not infinitely fast and becomes untenable to play. As you can see, it's already becoming a little bit difficult for me to play. But by essentially, yeah, see, it's getting really difficult. I can't even hardly play. Okay, we're getting barely there. I'm going to lose there. Okay, and then so it gets restarted. But you see, I have 1,300 points from breaking all these higher tiered colors, these higher colored bricks. And that's sort of one of the aspects that makes this really cool. Not only do we have visual variety, but this is going to impact our gameplay. So if we go over to our source code here, oops, I was on the right screen there. If we go over to our source code, So this all should probably happen within the collision part of the function. So that's going to be in the play state. So we go over here. And then we'll notice that now we're also doing a bit of multiplication here. So the tier of the brick, which we haven't seen quite yet, but if you're at a higher tier, you'll see gold, silver, bronze, whatnot. So whatever the tier is, in the case so that it's not any tier besides normal, it's just 0. So this is going to add 0 times 200, which is fine for right now. And then whatever the color is times 25, which I alluded to. So that's where we're getting the sort of higher level multiplied point total based on the color. But also in brick.hit, if we go back to brick, we'll notice that we have a little bit of logic here. So depending on what our tier is currently going to be 0. So for all intents and purposes, we don't have to fixate on that too much. But essentially, that's just going to shift the ball back, or the brick back, a series of colors, 5 colors backwards in the list of point values, because every tier is 5 bricks of color. And then here, that's if we were to go back in tier. If we were to look at self.color here, if it's equal to 1, which is blue, it goes blue, green, red, purple, I believe. Blue, green, my memory is a little bit fuzzy on the exact colors. But essentially, if it's 1, which is blue, well then, okay, that means that that brick needs to be no longer in play. And that's assuming that we're in tier 0, which is currently what we're at. If we're in a higher tier, then we're going to start back at the highest color of the next tier down, which will be like purple or whatever color is highest tier. And then we're going to also, if it isn't 1, let's say it's green or it's red, it's going to be 2 or 3 or purple or whatnot, then we're just going to subtract 1. 2 or 3 or 4, which is purple. But essentially here we're just going to subtract the color. And so that's going to then impact the score calculations and so on and so forth. And that's all we essentially have to do in order to get things working properly with the tier update. Now, one of the funnest parts of this lecture, I think, is the idea of particle systems. And particle systems are really cool because they're essentially just a way to sort of add this visual flair. And they're called a system because the particles that are inside of this sort of like emitter or generator kind of have behavior that you can configure. And so as you can see here, there's an example of the ball hitting what was a green brick, but it's got these green these green little blurry pixel things, particles that are emitting from that center, and they're purposefully colored green because the brick was just green. So it's kind of just, trying to keep in line with the coloration. But right now, when we hit bricks, they essentially just disappear right away. And there's some element of just simplicity to that that's a little bit jarring or unnerving, or maybe just unsatisfactory. But this is, I think, a way, and particle systems in general are all over the place if you're paying attention in games. It's a way to add just a little, literally, sparkle to your game in a way that adds polish, and I think is just kind of fun to work with. But they're quite complicated and intricate in terms of just the number of tweakable parameters that you can mess with. In today's example, we care about just a few fields, a few functions that we'll take a look at. But to create a particle system, it's just love.graphics.new particle system. Particles can take a texture. They do take a texture, which is, in this case today, we're just using some simple circular texture that you saw, some very simple small 4 or 8 pixel texture. And it's going to then apply various alpha and colorization functions to those particles, emit them in a particular way, fade them out, and so forth. And then that's how you can get the appearance that you want. But if you imagine creating like a diamond-shaped texture that you use instead, well, now you can give it this sort of sparkly, kind of cool, glittery effect. Or you could create like a fire-looking texture or something, which might look kind of hokey now that I'm visualizing it. Fire usually often is just a collection of particles, I think, anyway, in a lot of games. But you can sort of use any texture as the point that you can then apply all these other colorations and various things to, and they're explained in more detail on the Love2D wiki. So let's take a look at how those look and how we can add those really quick. So if we're in Breakout 8, which is where we're going to be, I'm going to go ahead and close Other here. Let's just run it so I can show you what it looks like. So it's going to hit one of these blue bricks, and it does indeed destroy it, and also it's got like a little blue puff of smoke, which is kind of fun. See if it can maybe, starts off a little bit slow, so used to how fast it was last time. But let's just give it a little bit of speed there. blue again, see if we can get it to be green. Might take a second, which we can. Oh, there we go. We got a lot of particle systems there. So each of these bricks is essentially given its own particle system, and a particle system will just be triggered to emit its particles, and we're setting it to emit about 64 particles here. And then they all have a decay, they all have a lifetime, at which point, once that lifetime has gone by, they'll all be completely removed, and then it will just essentially reuse the particles that it's buffered in its particle system. And just with that small change, now we have this sort of visually appealing way to give us feedback that we've actually collided with a brick. And this is done in the play state, just like we were looking at last time. So if you go to states, play state, in the, actually no, sorry, this might be in the brick hit function rather, which is called from the play state. So if we're in brick and we look at the brick hit function, so first off, I'm going to just point you to the fact that we have a bunch of palettes of colors here. So I've gone and hand-picked out through color picker or the like, colors from all of the various bricks so that we can match the colors of what the particles will be to those exact bricks. So we have approximately the RGB for all of the brick colors here, red, green, purple, gold, blue, so on and so forth. And you notice that we are declaring a new, as a state variable in every brick, it's going to have a reference to its own particle system, a new particle system. It takes in a texture. We just give it texture of particle, which if you were to look at it, it's this very small, sort of, it might not even look like anything meaningful. If we look at it, just a very tiny, it almost looks like something you'd see if you were scrolling through metadata or icons oh, whoops, didn't mean to hit that one. But it might just look like a little, got to scroll in a lot to see it. But it's just these pixels here. These are just what your particles, the particles that we're seeing here are made out of. It's just a very simple grayscale so that when you do apply color to it, it's very clean. It doesn't have any pre-existing colors or anything like that. But you could make this literally any texture you want to, and it will just spawn a bunch of those instead of this little sort of roughly diamond-shaped circular particle. So I'm going to go back here. So we are creating a P system, short for particle system. I've commented this out a little bit, but there's a few functions here. We have a lifetime that we're setting on the particles. All of these are documented in the Love2D wiki. So between 0.5 and 1 seconds of lifetime, that's how long the particle, each individual particle will live. A linear acceleration from an x1 and a y1 to an x2 and a y2, and it'll be variable between those. So it'll be some x between -15 and 15 that it moves. It's going to have a linear acceleration in a particular direction while it's fading away. And then it will only ever be between 0 and 80 on the y-axis. Recall, the particles are kind of falling down, sort of like glittering down, almost like there's this artificial gravity that's applying weight to the particles. And so we accomplish that with a linear acceleration that can only be positive on the y-axis through this. And then also the emission area, which is sort of like the radius around the center of the particle system where it can actually be, where it can spawn particles, so roughly 10 by 10 pixels in this case. And then the standard deviation will be 10 pixels away, x and y, so within that radius roughly. And then what that's going to do is essentially we've pre-configured the particle system. It just has to actually call it. Now also, to set the colors, there's a set colors function here, which we're just passing in the RGB between the color that we want to start at and end at as two pairs of 4 color components, so RGBA, RGBA. We want it to eventually fade out to completely alpha transparent. So we're just doing that here by setting this alpha to 0 for the second color. It's going to be the same color, but just faded to alpha transparent. But you could, in theory, you could choose one color and have it fade into some other random color if you want to. Particle systems are very flexible in the sort of ways that you can use them. But we're essentially going to multiply by our tier so that we're like more saturated on higher tiers with our particles for our alpha component for the first color that it starts at. And then we're going to fade towards essentially transparent. And then P system : emit of 64 is just going to actually shoot out, it's going to actually emit those 64 particles that we've pre-allocated and trigger the actual operation of the particle system working. And that's all you have to do in order to get a particle system to work. They're very intricate, complicated. They can be very dynamic and have a lot of cool behavior. But for this example, we're just doing a sort of like little glittery sort of puff of particles, and those are some of the functions that you can use to accomplish that. Okay, going to take a brief water break.
Nice.
So with that, we've added some visual polish to the game, but there are a few missing states still in our game. If you recall, looking at the very beginning of the lecture, we had this large state diagram. We had a few states still that we have to talk about, and so one of those is the sort of level or victory state, rather. So whenever we finish a level, we want to display a sort of level X complete or the like, hence the sort of the little illustration there with those few slides. And this also represents progression, because with every sort of victory in your game, you can have a new grid of bricks that you make progressively more and more difficult, which we've been alluding to and talking about. But this is really important because now, we can sort of have something to aspire to. Oh, I made it past level 5, or I got to level 10. And it's random here every time, so you could play this a lot and kind of always see a different game, right? You might get something very easy, even shown in the level 2 there is actually easier looking than level 1. But I mean, if you look and see, level 2 does have purple bricks, whereas level 1 only has blue and green. So in some sense, it's kind of, relatively equal, I suppose. But why don't we go ahead and take a look at Breakout 9. And we transition to that. I'm going to close all of these. And then close this, Breakout 9. Now to test this, we might have to clear a level. That might be too long of a level. I'll try to maybe get a shorter one. We'll see how our luck is. More doable. Let's see if I can get a single line. I'll just do 1 or 2 more iterations. Okay, that's much better. Okay, maybe. We'll see. But these are purple, so they'll be a slightly longer, have to hit them a few times, but we're going to have a score. So let me get the velocity going really high. Hopefully I don't lose. This would be embarrassing. But essentially what we want to do is we want to have the score go into the victory state, just like any other state did. And then we want to have the, maybe I'll just actually try one. I want to see, just get a full blue one. Give me a full blue. It's the one downside of having completely randomly generated levels is if you want to hard detect something, it can be slightly, oh, yeah, definitely not that one. We can have some fun looking at random levels, I guess. Oh boy, now see, that one is actually kind of cool. That looked like a castle, actually. Okay, one more time. Okay, much better. Okay, this should be reasonably fast. So we'll just keep doing this, and then we'll try to get a victory. But essentially, what we want is not only do we want the state to transition, right, to create a new level, which we're going to do, but also that level, the actual tier of all the bricks, the max tier and everything and so on. Oh, there we go. Yeah, there we go. That's what I'm talking about. Oh, and then I lost, of course. Let's see if that was convenient there. Well, we want the game to get harder with time too, because that's part of what progression means. It ultimately means not only do we, okay, come on, please. This oh God, this would be so embarrassing if I lost. Okay, we just one more. Okay, this fingers crossed. Is this gonna be a victory? Oh. Yeah, okay. That was a very lucky shot at the very end there. But as you can see, we have a sound effect. By the skin of our teeth, we survived somehow on level 1, which is embarrassing. But we have 650 points. Level 1 is complete. And we can press enter to serve again. So now this is sort of like the illustration of what it means to have progression. Now, if we were to press enter now, the game is going to store the fact that we're in level 2 and not in level 1. So if I press enter, now we're in level 2. Notice that. So we're in the serve state again, a much bigger playfield in this instance. But this is sort of how we do progression in games. If you have levels, and we'll look at something like this in Mario, even though in the Mario examples you might not use levels, you could apply the same idea. It'd be part of the Mario problem set. But you could take the same idea and then just in some way make your game state, your world state, slightly more difficult, some variable or set of variables that will lead to this feeling that, okay, I am progressing, I am going further into something more difficult. And it's one of the most important things that you need, I feel like, in a game for it to be engaging and fun, and something for me. I definitely need something to aspire to in the game. And so this idea of, oh, I beat level 5, or I got to level 2 or 3 or 4 or whatever, can be very valuable. So let's take a look at the code of where we're doing this. This is ultimately a pretty simple thing. So if we're in the play state, recall the transition is from the play state to this victory state. So if we go to the play state here, and if we have cleared out all of the bricks, so let's go up here. So we have this function called check victory. We're defining it as a method on self on the play state. So check victory is going to do what it needs to do to determine, oh, are we ready to transition, which is just going to be, are there no bricks left, or all the bricks not in play? And then we can change to victory, passing in our level. We need the level because we're in level 1. We need to pass it in to say, okay, the victory state knows we're in level 1. Let's increment that to 2 and pass that to the play state so that the level maker can now get past that variable and then make progressively more difficult levels, and then keep passing in the other details as needed. So if we scroll down just a bit, we'll see the check victory, which is a very simple function, which is just for all the bricks in self.bricks, like if any of them are in play, return false, because that means we know for sure we aren't ready to transition to victory if we still have a brick in play. But if we've gone through all of those and none of them were still in play, well, then we can return true. We have indeed reached our victory state. And so if we look at our victory state itself, we'll see that it's relatively simple, but it takes in all of those data, pieces of data that we just passed in. We just looked at those. And then we can still update our paddle, but when we do, this is the important part, when we press enter to change over to level 2, we're going to increment self.level plus 1 as we pass it from this state into the next state, into the serve state. Serve state's going to take over this level variable, which is incremented here in place. And also bricks is right out the gate, because we need to see the bricks before we even start playing. It's going to be passed in also that self.level plus 1. So now the level maker knows, okay, we're in level 2, also generate maybe slightly a more sophisticated map. And that's essentially all you need, right? And in addition to, of course, the rendering here, which says, okay, level X complete, where X is self.level, and so on and so forth. But that's essentially all the code that we need. And now we have progression. We have levels. We can keep going and feel like we're actually aiming towards something and getting higher and higher scores and more difficult grid layouts. So that's the progression update. The other important piece, the last sort of remaining thing in the whole game, is the high scores. We saw that at the very beginning. High scores were at the very beginning of the game. We didn't really talk too much about them, but we sort of already see that we are preceded with all of these different variables. This is a screenshot taken from a different time where I had just created a bunch of random scores, and it was playtesting a bunch of times. CCC and CTO, just different alternations of my sort of initials. But essentially, there are a few important functions that we need to talk about, and these are all tied also to the idea of data persistence. If you think of any game that you've ever played on console or whatnot, I mean, a long time ago, back in the day, you didn't really have persistent data. Look at like Nintendo or Game Boy. Most Game Boy games did. But if you look at like Nintendo, for example, a lot of games didn't ship with a save file. Legend of Zelda was one of the first that did, which was a battery that kept a certain amount of memory active so that it preserved your save data. But generally nowadays, with modern computers, we expect these to exist in games. And essentially what we need to do is think of, I need to save a file on my disk that can store something like all of my high scores. And with that, then I can, when I start the game up later, I can load this file from disk and then display them as if they were just always there. And then this allows us to, in the future, we can just keep aspiring for higher and higher scores. It's a little bit deflating to think, okay, I'm going to work put all this time and effort into playing this game and just completely lose my high score. And so I think this is a very important thing that we should incorporate into most games, this idea of data persistence, save files. So there's a few important functions we need. Love.filesystem.setIdentity is just sort of a way to say, okay, where at should I assume I have free reign for a folder to put save data in. And so by default, this is in some folder on your operating system. Like on Mac, it's your user folder, library, application support, and then whatever folder name you put in as your identity. On Windows, it'll be in your app data, local roaming, something like that. And then on Linux, it's in some other directory. And this is going to be variable dependent on your operating system. You can look there based on this identity key that you've passed in and find the sort of save data that's going to exist there. And then there's a few functions that Love gives you, sort of like basic operating system functions. You can check to see if a file exists with love.filesystem.exists at path, love.filesystem.write, so you can actually write at a path a file, some data. And then love.filesystem.lines, which just it enumerates over the new line spaced lines of text in a file, which is for our intents and purposes what we're going to need to save our data. We're just going to think of it in terms of, okay, for every save file, or every high score rather, in our program, we want the initials, of course, but then the score. So we can just think of every individual high score as that initials and then the score, sort of like blocks of 2 lines separated. And we'll just iterate over that in a loop. Just divide by, get all the lines, and then just like, okay, from 1 to the number of high scores, which is 10, grab that line, grab the next line. The first line will be the high score initials, the next line will be the number, and then just go to the next iteration of that loop. And then that'll essentially load all of the high scores into memory. So why don't we take a look at how that looks in code just real quick. Pretty simple, ultimately. I'm going to go ahead and open up Breakout 10. So if you close this out here, Breakout 10, main.lua. So in main.lua, we have this function called load high scores, and this is going to get called at the beginning of when we run the program. And so if we come up here, we'll see that when we actually trigger our G state machine to change to the start state, we're going to seed it initially with all of our high scores. And this will be some piece of information that we just can pass back and forth between all the states. So when we get to the victory state or the high score state, these will be in memory available to us. We're going to load them at the beginning of the game. We want them here because if we click on high scores, we're going to want to be able to see them. And when we hit start and then go to the play state and do all of that stuff and then end up getting into a victory or game over state and then losing, we're going to want to check, okay, is the score that I ended with higher than any of the scores in the 10 high score table? And if it is, okay, well, I know that like I was above person 8, so like I need to replace 8, and then 10 is going to get booted out, and then 9 is going to get essentially shifted down, and then so will 8. 8 will now become 9, so we'll take over 8, and then 8 and 9 will become what were 9 and 10, and that's essentially how all sort of score rewriting is going to happen. You look for whatever the highest index is that you exceed the score of, shift all of them down by 1, and then replace whatever was in that spot effectively with your score. So if we go back down to load high scores, essentially what we're doing, we'll do that in the victory or the game over state, assuming that we actually get a high score. But you can see here we're setting our identity to Breakout. So that means there's a folder that's going to exist called Breakout in that file system sort of directory that's operating system dependent. And then we're going to check, okay, get info on breakout.lst, which is just a function that we'll check to see, is there a function that exists there? And then we're going to say, okay, there's a string of local of scores, and then this is essentially what's going to be all of the scores that we load from memory, actually. And then, actually, sorry, in this case, this is going to be what we initially seed all of the scores with if no scores exist, rather. We're looking to see, okay, did we actually save a score table before? If we didn't, that means that we are loading it for the first time. And then so what we're going to do is we're going to generate a list of 10 scores. In this case, I've preceded it with just my initials here, and then just I by 1,000. So we'll start at 10,000. We're iterating backwards. For I gets 10, 1, -1. And then we're going to just add a new line between not only the initials, like I said, it'll be initial score, initial score, initial score, 20 lines of text in the code in the text file. And then once that's all done, we're going to just write to breakout.lst. We're just using LST as a general sort of extension to represent the fact that this is a high score list. This is arbitrary. You could call this whatever you want. You could call it .txt. You could not call it anything. You could call it .dat, whatever you feel like. .lst for .list of scores. And then what we're going to do is we have this in text, but we need to actually turn this into code. So what we're going to do, a table of data that we can actually look at and then shift sort of in memory and displace depending on how we do with our scores later down the road. So we're just going to essentially create a sort of 1 through 10 indexes into scores, this table, which starts off with name equals nil, score equals nil. Then we're going to load that same file that we just created it or it existed before, and then we're going to just populate that in memory, just like this. And so eventually that's going to mean that we have just this set of data that we can use to reference in our victory state, rather in our game over state, and compare and shift names and scores based on did we actually beat any of the high scores, which is very relevant for being able to actually beat our prior scores. So we'll go over to states. We'll go take a look at game over state, which is where this is going to happen. Or rather, this might happen in the victory state, not victory state. This might happen in the high score state. I thought this happened in the, shoot, okay, let's redo that. I got tripped up. I thought this happened in the, oh, because we don't do it in this example yet. We do this in the next example. Okay. Okay, let's approximately, Julie, do you have a visual on what my editor looked like? Things are going smoothly for a bit. So with being able to now store all of those in memory, that's the first step towards being able to have our high scores sort of usable. But the other part of it is that typically, you know, when we are looking at high scores and being able to add them or change them, you do want a way to input your initials. And so that takes us to the entry update. So we can now write files. We've looked at how to write files, look at files, store them, actual scores in memory, but we still need a way to edit the initials for if we want to save our score. If we can't actually save our name to anything, well, we can't actually update our high score. So I'm going to open up Breakout 11 now to show that. So I'm going to close out this. Let's close that, open up Breakout 11. So we looked at the sort of high score loading function, and that gets passed to the start state. Now what we want to do is take a look at the game over state. So when we actually get a game over, this is where we can decide, okay, should we go to the, there's going to be a new state here because as we saw, this UI for inputting our initials, we're going to need a way to do that and show that. And that makes itself very ideal for a brand new state. So we'll call that like enter high score state. And the place to do that, to make the determination, is going to be in game over. Once we hit an actual game over, that's like the game's done, whatever our score was, that's the time to decide, okay, should we actually go to the enter high score state? Because remember, when we talked about the state machine at the very beginning of the lecture, if we aren't a valid high score, if we haven't eclipsed any of those scores, we probably just want to go back to the start state and then just begin playing again. Let the users press enter. Maybe they can look at the high scores again on their own time if they wish. So in the game over state, when they press enter, that's where we're going to mark an actual transition point towards either the high score state or the start state. And so we just do some math to basically work our way down, up through our high score table, which are always passing back and forth between all of our states. It's just a parameter now that we pass between changes. And so we can say, okay, self.highscore is at i.score. Remember, 10 from 10 to 1. So we're going bottom up, lower scores to higher scores. If our self.score, which is another piece of data that's being passed between states, is greater than that, well, okay, that's what our high score index is for now. And then we're going to set high score to true, meaning we got a high score, we should transition to the enter high score state. So if high score, and we'll just keep doing this, this will go all the way up to 1 so that we can, because we might, we'll be higher than maybe multiple scores if we start at the bottom and maybe we got 5,000 in the pre-existing version. That would put us at like about position 5. And so we want to go down to here. We want to let that process keep track of what the highest score is that we were. And then what we're going to do is we're going to say if high score, let's go to the enter high score state. So let's go ahead and open that up. So enter high score state. Now this is a relatively light, somewhat simple state. All it does is it takes in those values that it cares about: high scores, score index. It needs to know at what point was this score higher than any of the other scores. And then also what were the scores, of course, so that it can shift them, and then it's going to resave them to disk. So it's going to end up, actually the UI, as we saw, is some sort of like letters that we can move up and down. And in fact, we might be able to quickly demo this and see, we can actually lose this deliberately, but this has been pre-seeded to be more generous than normal. So we should be able to, let's see, Command L. We should be able to quickly get a high score. So look at our high scores. Our high score is at 10,000 to 2,000. So I'm going to go ahead and start. And then we're already at 3,000, actually. I've gone ahead and pre-seeded it. So I'm just going to deliberately lose a few times, if I can. Oh, that time it got right on the edge and it clipped up. But let's see if I can lose a couple times really quickly. So I can show you what this UI looks like visually. It's going to use similar logic to actually what we use at the title screen, which is this sort of up and down sort of cyan highlight appearance. But see, now we got 3,175. Recall, we started about 1,000 going up to 10,000. So I press enter here. We got like a sound effect that plays to show that we're in a victory. I can press left to right, and that will allow us to sort of move through these letters. We got a sound effect that's playing when that happens. If I press up, you can see that we are actually rotating through letters, and these letters are being represented numerically. So we're using ASCII for this. So 65 represents A, capital A. So what we're doing is we're going to just press up and down to increment through these ASCII values. We've got 3 numbers that are being stored that are being converted to strings. So we'll just say C. Yeah, I guess enter actually saves it. I was thinking move left to right with enter. But in this case, you can see that we are just above position 10, which was at 3,000, and we've gone ahead and our new initials are there, CAA. So it went back up, it iterated through the loop, through the table where all of our scores were, and then it ended up just putting me right where 9 was, which was the number below that, which was 3,000, which was the CTO there. That got bumped down to 10, and so now we're actually in our high score table at 3,175, which was the score that we ended with. And so if we, in fact, restart it, we should see the same number, the same high scores there. This is being saved in that .lst file right at the time that we save that. if we go ahead and, oh, it looks like it is stalling for a second there. We'll go ahead and transition to this here. I'm going to go ahead and load up that'll be in the enter high score state. So when we press enter, so also visually, I just want to show this here too. This is where we're actually changing the color of our pen for which letter is blue versus white. So if highlighted char is 1, so there's going to be a highlighted char. In this case, it's a piece of state. Highlighted char is just, okay, first, second, or third character. Which one are we editing? Which one are we changing the initials of? This is a very sort of common presentation for arcade games and games of that nature. So we start with obviously just the first character, which is the character most on the left. In AAA, it's this first A that's here. And then if we press left or right, we'll shift through that. So that'll turn highlighted char it'll increment it. So it'd be one of these conditions in here. So right here, if keyboard was pressed left or right, we'll go ahead and we'll just increment highlighted char -1. And also we're making sure to clamp that. So if highlighted char is greater than 1, we only do that. If it's not, then we're not going to do that. We're just going to keep it linked or keep it limited to the left and right space. So we can't go less than 1, we can't go higher than 3. And then up and down does a different thing here. Here it actually will increment numbers that we're storing at this chairs or cars table that we have, or chars table, at highlight char, so 1, 2, 3. It's going to store a number, so that number is going to be between 65 and 90, 65 being the letter or the number that represents A, 90 being the number that represents Z. And so we can't go any higher than Z, we can't go any lower than A. So that's essentially up and down. We'll also be clamping here the values that can be represented by those letters. And so if we render those, we'll see that Lua gives us this string.char or string.char function, which will just take in a number and it will give us back the string for the character that is represented by that number just by calling that function. So that's a function that Lua gives us as part of its string namespace globally that we can use. And so once we press enter, it will finally trigger this code, which will finally actually take the name by concatenating all three of those. Cars 1, cars 2, cars 3, it's getting the string.char from those. Using the dot to string concatenate them to make a name. It's going to then ultimately put that into wherever in our scores table was the index that we determined we were higher or equal to. It's going to put that in there with our score. And then ultimately, it's going to save that to our file. It's going to just create a string. That's what we're doing here. We're just going to keep adding to a string from 1 to 10, all of our table entries, just initial score, initial score, initial score, a brand new .lst file. It's going to save that. And then once we're in the high score, once we've finished that process, it's been saved, we can then change over to high scores, the other state, which we looked at previously, which is just a very simple iteration of our high scores table. As you can see here, from 1 to 10, just go ahead and display all of in a formatted table, sort of visually using printf in a way that looks somewhat sort of structured. We'll display all 10 of our high scores. And that's all you need to display high scores. At that point, you are completely ready to go. The last sort of example that I think is fun, besides sort of music, which we'll add at the end, which is trivial, is this idea of paddle select. So this is kind of a fun thing, just to get us a little bit more UI. We won't spend too much time looking at this. Just to polish things off, we have all these bricks, we have the balls of different colors, but let's just actually maybe allow us to have a different colored paddle too. Why not? We have the textures there, we'll support it. So I'll just show what it looks like. I'll go ahead and run this, make sure that this prior one closed, which it did. So we'll go ahead and just run main.lua in breakout 11. Oh, sorry, breakout 12 is the one that I meant to grab. 11 is the one that allows us to enter our scores. Breakout 12, I'll go and open. I'm going to close all of these to start with. And then main.lua. When I start this, we'll now have this sort of UI. We've got these buttons here on the left and right. It's sort of like, okay, if we're at index, sort of almost think of it like the letters we just looked at. We can't go higher or lower than a certain index for colors for our paddles. There's only a few different colors. There's blue, green, red, and purple. So 4 different indexes, 4 different colors. If we're at index 4, we can't go further to the right, so let's gray out that image. If we're on the left, we can't go, or if we're at index 1, we can't go any further to the left. Let's just gray that one out too. So let's just choose red. that piece of data is like the skin variable that's now on our paddle, and it'll carry over throughout all the rest of it as we're playing. And it's just sort of like a fun thing. It just sort of allows you to feel, I guess, more personal about your game. I mean, every game on the planet nowadays has just a million skins and just various fun things to do. So there's some personalization in there. It can be kind of fun. If we just take a quick look at the state, what the state looks like, relatively not a whole lot of things we haven't seen yet already, so we won't spend too much time on it. But it's a new state, paddle select state, which will now precede the actual start state. So if we go over to the main.lua, we'll see when we do a transition here. Rather, start, actually, I should say, goes to the paddle select state. So for in start is the menu. This needs to happen after the menu. So you'll start state, then paddle select, then serve. So if we're in start state and we press enter, which will be here. So if we're highlighted on 1, now we go to paddle select. We no longer go to just straight to serve. So if we open up paddle select, we'll see it's pretty simple. It's ultimately just, remember, we're keeping around the high scores. Let's get passed back and forth between all states. But paddle gets 1, current paddle is 1, and then depending on what we choose, that's a piece of information that will eventually be passed in to when we do a actual transition to the serve state from here on out, because that piece of data needs to move between the states. We'll just go ahead and we will instantiate our paddle right off the gate here, and we'll call self.currentPaddle passed in as the parameter for paddle, which ultimately, if we look at paddle again, the first parameter is the skin, and then we'll just save that as a variable here, so that whenever we draw paddle, we're just going to index, we're going to offset our drawing index again with a quad. Instead of drawing blue, which is the first index, we'll draw, if we choose red, it'll be whatever 3 down is, and we're going to multiply by 4 rectangles that way. So we skip all of the different versions of blue to go to green, to go to red, to go to purple. So we're sort of like using skin as a multiplier on indexing into the quads table that we looked at previously, which if we were to go down to render, we'd see that happen here. So self.size plus 4, which is the sort of like ultimately the self.size plus 4 times the skin minus 1. So that's going to end up being like your size is your index into the 4 sizes per color. We started with size 2, so we'll always pick the second of the 4. But then we want to also multiply that by whatever the skin was, but we're going to minus 1. So it'll be 0, but then if we're on blue, but then if we're on red or green, it will just end up actually shifting the overall index that we're in, whether it's 2, or if we wanted to play with a larger or smaller paddle, it will essentially add multiples of 4 or subtract multiples of 4 from that to give us the correctly colored paddle in our image. If we just pull that up for memory's sake here, and we look at breakout.png, you'll see that there's going to be 4 rectangles, 4 paddles, and so that's what the skin essentially does, is it acts as a multiplier. You do 1, 2 for size, and then depending on which skin you choose, it'll be it'll be your skin times 4 added on top of that. So 0 for blue, and then 1 for green, 2 for red, 3 for purple, moving 4 rectangles into that list of rectangles that we generated earlier on. And so that's how you can create a state that allows you to choose your rectangle skin. And then the very last update, just to round things off, the music update, which is going to be, I didn't have the slide thing set up here, but so the music update is very trivial, very simple. We're just going to go ahead and, for the sake of rounding things off, we won't even need to dwell too much on the specific details of that, but I'm just going to go ahead and run main.lua. I liked the music track that we found for this, but, I need to click on that. So for some atmosphere, we'll play, just goof around a little bit, just play with the green paddle. Start at level 32 just for fun as well. Typically like to, just to see what it generates. Okay, not a whole lot of delta. Let's just bounce it like that a little bit. Oh yeah, there we go. Clipping at all the corners, there we go. Yeah, there we go, give it to me. Yeah, that's good. Okay. And so fast that I can't even handle it. But yeah, we got 4,475 points that way. So ultimately, we have a very exciting, final product, final thing that we've created. It's very colorful, it's very musical, but ultimately that wraps up Breakout and its sample code. And so some of the things that we'll look at next time, so this time was a lot of stuff. So very few lectures I think will have quite as many details and a lot of things to take in all at once, but Breakout is probably the biggest hurdle stepwise in difficulty, I would say maybe throughout the term. There will be other things we look at, certainly, and Mario and Zelda have their own difficulties. All of them have their own things to look at. But Breakout is probably the biggest jump up to feeling like we made a full game, rather than Pong, which is kind of simple and two-player, and then Flappy Bird is single player, but also very simple. Breakout's got a lot of pieces to it to make it a good implementation. So next week we'll look at, we already looked a little bit at anonymous functions, but they'll come in handy particularly next week. Tweening and timers are very important things. You've noticed probably that all the things we've done so far have been very physically modeled, in that we've got a ball and maybe some paddles and things like that. It's bouncing off of things. We got velocity. But if we want to say, okay, move this thing over here over a second or over 2 seconds, we don't really have a very easy way to do that right now. But there are ways to do that with convenient features to say, okay, let's take some x value and sort of interpolate it, for example, over time to go from this position over to this position. And now we can say, okay, over 1 second's worth of time, why don't we move this thing over? And now we can start to model all kinds of cool visual things that we can't do so far with just physics. We'll have to look at discrete sort of problem solving in a context of a puzzle game, because, spoiler alert, next week's lecture is on Match 3, aka Candy Crush, or Bejeweled, which is something that I think a lot of folks probably have familiar with, especially similar to Flappy Bird, folks that are playing on mobile. We'll look at more ways to doing, that's sort of baked into those games is this idea of this randomly choosing shapes to fill in and how to make a procedurally generated, so to speak, game grid of tiles, be it candy or gems or whatever. Next week it will be sort of these tiles that almost look like vitamins, but they look pretty nice. And then we'll also take a look at sort of sprite art and palettes and the influence that those have on games. And so assignment 2 is going to be kind of about extending things. Most assignments are about extending things in sort of ways that I think are intuitive and make sense. Right now, as in a lot of Arkanoid or Breakout instances, right now we don't have anything that changes the player's paddle size, even though we saw paddle sizes and whatnot. We don't have things that influence, for example, we saw by default the ball was sort of going through bricks just on its own, or fully without colliding with anything. And that might be some sort of special power or God mode or the like that you could activate through a power-up. And so you might want to add something like that. In the case of this problem set, it's going to actually be spawning multiple balls, sort of like a pinball-inspired mechanic where instead of just one, now you have two. And if one you lose, that's okay. As long as you have one ball in play, you're still technically okay, and you can clear the screen sort of twice as fast that way. And also, we should have a way to grow and shrink the paddle based on if you've gained enough points. And there's already an implementation to recover health built into the problem set if you've gained a certain amount of points, and that amount will keep going up. But if you gain enough points, then maybe you can just grow your paddle for a bit. You've deserved a sort of boost to your strength for not taking damage for a certain period of time. And then lastly, and we sort of looked at that in the sprite sheet, adding a lock block. And then a key will maybe fall down from the ceiling. And if you grab the key, you can then now hit that block with the ball. And if you try to hit it otherwise, it just won't unlock. But that was essentially Breakout. It was I think, again, probably the biggest jump in the course in terms of overall complexity and difficulty. But I think the things that we looked at today, in particular sprite sheets, will help simplify projects tremendously going forward. And they'll also segue us nicely, into next week for Match 3, which has bricks that are also all in a sprite sheet, but also for animations, which, spoiler alert, we'll be looking at a lot with Mario and Zelda and other problem sets. So that was Breakout. This is CS50. We'll see you next week.